the society is chaired by Eduardo Martin Martinez. So this cost action has been the main funder of the conference and has played a major role also in its organization from a scientific point of view. So the members of the scientific committee are Haris Anastopoulos, myself, Aleo Shamma, Fedele Lizzi, Giampiero Mangano of our university, then Natalia Moller, again Rick Perch, Dennis Retzel, Kasia Reisner, Daniel Terno, and Villasini. Okay, so as I said, this is the oldest state university in the world. It was founded by Frederick II, Emperor of the Holy Roman Empire, and also King of Sicily, King of Italy, a lot of things. Actually, the first building is quite recent. It was built at the turn between the 19th and 20th century, whereas this part belonged to the College of the Jesuits, which has then been transformed into university. The CEO of the university before that was around Naples in many monasteries and different places. So these two rooms, I will tell you something about these two rooms. They are twin rooms. This is Aula F or Hall F. F like physics, and the other one is Aula C, C like chemistry, chimica. And I will tell you something more. So most of the time we will be here and there. The plenary session will be held here, but if we need space, room for people, people can also sit there and watch the conference and ask questions, whereas the parallel sessions will be held one here and the other there. Except the plenary session all here except Thursday, where we'll go to the Accademia Pontaniana, which is also very close to here. So the place where we will have lunch breaks and coffee breaks is the Cortile delle Statue. On the way to Cortile delle Statue, there is this Accademia Pontaniana. And now this room is, I mean, not in the best possible state, but it's a historical value. It's the room where Ettore Majorana held his first lectures when he came to Naples. And it has also an historical value for most of older physicists in Naples who studied here, at least the first 2 years. We got the lectures of physics. And this is how it looks full. It's a class for university lectures. But I should say that during exams, it transformed into something else. It reminded us of the Dante Inferno, because the form more or less is like that. So here, Satan was sitting and punishing all damned people in the various circles, and so on. Okay, so this is more or less the map of the place. You can see there is here the entrance to the university. You have crossed the place of guards. Then this is the stairs. And the two rooms are here, F and C. Now, very important thing, toilets. Where are the toilets? So there are certain numbers of toilets here. So you have to go down the stairs and turn left. So T for toilets. And then there are other toilets here on the way to Cortile delle Statue. So this is the way to Cortile delle Statue and to Accademia Pontaniana, which is here. This is Cortile delle Statue, okay? We will go together for the first coffee break there. So among the gadgets, there are these mug cups. These have been made in Vietri, which is a very nice village on the Amalfi Coast. And they have been hand-made, hand-decorated. Also the writing, all writings are different, one piece from the other. So this is also a way to say, if you go around after the conference, you will see a lot of things. You have many opportunities. Naples has a very large historical center and was one of the most populated cities in Europe until recently, the second most populated. Inside this huge historical center, there is a so-called ancient Greek-Roman center, which I have here encircled, which was the city founded by the Greek and then transformed by the Romans, which is practically starts here. We are at the edge of the ancient city. Corso Umberto was more or less where the line of coast was. The sea was closer. And then you have this marvelous ancient center, which preserves the original structure. So there are three main streets going east from west. West, they are called decumani, and then perpendicular ones are the so-called cardines. This was used both by Greeks and Romans as a very normal and rational way to organize the city. So nowadays streets are almost all on the same track, and in many different places you can go down and see the city as it was there. For instance, well, just to mention two quite large and well illustrated places, Napoli Sotterrata and Napoli Sotterranea. We won't have time to do a tour in this part of the city because the schedule is very tight, but before early in the morning or late in the evening, you can visit something. And this is possible because we decided to hold the conference, in this historical center instead of some other more logistically easy place like the engineering faculty. There was a debate among us. So from the logistical point of view, this place is not the optimal one. It's also a bit warm, not to say hot. We hope it won't be too hot. They are still doing something which should have been done before. But at least you are in the middle of the center and you can look at the incredible city of Naples with its vitality, its many different faces all around. And everybody of us of Naples will give you suggestions if you like. As you know, on Thursday we will do only one excursion. It will be a boat excursion starting from Molo Beverello here, and we will go around along the coast, which is a really beautiful coast, until Miseno, which is over beyond Pozzuoli. And you will learn a lot of things, and I think you will be enchanted by the panorama. So, yes, these are just a few places you can see. These 1, 2, and 3 are in Naples, so this is instead in Pompeii. And all what I can say is that we hope you will enjoy this experience as much as possible. And so if Haris is there, no, not yet, okay. Anyway, is there anybody who has not applied to become a COST member or a member of CA 23115? You? You are encouraged, invited to apply as soon as possible. There is a preferred motorway for your access, guaranteed by Harris, and later we will tell you how to do it. One important thing. So, internet connection. So here there is EduRoam. But for those who don't have EduRoam, we have a special account whose name and password we now write here, okay? And, okay, we are in advance. Maybe we wait a few minutes before the start. In the meanwhile, I introduce Jorma Luko will be the first chair, and the first speaker will be Doreen Fraser. So we wait a couple of minutes so that you can connect and other people arrive, and then you can start with the first lecture. Prova.
So how about 35 minutes for talk, 5 minutes for questions?
Yeah, I'm going to try to be a bit shorter than that, but we'll see how it goes.
I'll give you warnings to the 35 minutes.
Okay, perfect. Yeah. Thank you.
So, both?
Give it back to me because I turn it on and then turn it off, and then this is needed for the audience that we're wasting time. So I'm gonna pass both of them.
5, 6. Good morning, everyone. Good morning, everyone. My name is Jorma Louko. I'm from the University of Nottingham, and I will be chairing this first morning session of the conference. Our first speaker is Doreen Fraser from the University of Waterloo and Perimeter Institute and Rotman Institute of Philosophy. And we have an all-encompassing title, History and Philosophy of Quantum Field Theory.
Thank you very much. Can you hear me with this microphone I have here? No. Okay. But this one should be on. Okay, I'll just hold it. Can you hear me now? All right. Good morning, everyone. Thank you for having me. So I'm not going to be able to get to all of the philosophy and history of QFT in this short talk, but I'm hoping to give you an idea of how I think that there is important lessons, context that we can draw from thinking about history and philosophy of QFT. So for those of you who I don't know already, I am indeed a philosopher. So my work primarily is in history and foundations of quantum theory. And as you probably are aware, quantum foundations is a field that's split between philosophy and physics, and so I'm coming at these issues from the philosophy point of view. So it's appropriate that this talk is the first talk of the conference because I'm going to be starting with the big picture question, classic philosophical question, why are we here? But I'm going to take a narrower point of view than often we do in philosophy by looking at the mission statement for the Society, which tells us that the Society provides a platform for interdisciplinary research on the interface of relativity, gravity, and quantum theory involving modern concepts of information theory. The goal is to address fundamental questions such as how quantum theory and gravity work together. So clearly, the real reason everyone is here is because this is non-trivial, right? This is a very challenging research program. And so what I want to talk about is some of the context to why it's difficult, and indeed why it's difficult to even take what you might think of as a baby step from getting quantum theory and special relativity to work together. So I think that the history and foundations of QFT, philosophy of QFT, offer some context for appreciating better what the difficulties are, challenges are inherent to this kind of project. Okay, so I take it that what people are trying to do here, at least in the first instance, before you try to take the larger step to gravity, is the diagram that would be on your right, to formulate relativistic quantum field theory and to put with it some sort of measurement theory. I'm going to contrast this picture of the dynamical theory plus the measurement theory with what we find and are all very familiar with on the quantum mechanical side. So NR stands for non-relativistic, ordinary quantum mechanics, which we all know how to pair with QMT, which is quantum measurement theory, usually called QMT, but it's specific to non-relativistic quantum mechanics. So what I'm going to do is I'm going to start by talking about an example from the very early history of quantum field theory for context, talk a little bit about the history of local measurement theory as a project for quantum field theory, and then I'm going to say a few words about the measurement problem for quantum field theory and interpretations of quantum field theory. Okay, so I think it's useful to go back to a very brief history of where QFT comes from. So again, this is just the initial stage where the goal is to unify the theory of quantum theory, ordinary quantum mechanics, with the theory of special relativity. So as we know, 1905, we have special relativity. Quantum mechanics comes along a couple of decades later. We're now halfway through celebrating the 100th anniversary of quantum theory with the original papers by Heisenberg and Schrödinger, among others. it's important to realize that, of course, since we already had special relativity at that point, quantum field theory was already a project which was envisioned at that stage, as soon as quantum mechanics was formulated and proposed in a very familiar form. In particular, you can think of Dirac, perhaps, as being the beginning of the project of relativistic quantum theory, publishing a paper the very next year. But it was non-trivial from the start. It took several decades before there was even a workable theory of quantum electrodynamics, which of course involved many false starts and trying to figure out how to both regularize and renormalize that theory perturbatively. So it wasn't really until about 1949 that even quantum electrodynamics gets formulated as a quantum field theory. Okay, so that already is an indication that there's something different about non-relativistic quantum mechanics and quantum field theory, and that the latter is a much more challenging project. So already in 1949, of course, there were important foundational questions that were raised by the success of quantum electrodynamics, which was very successful for practical, sort of empirical purposes, but the foundations were not clearly on firm ground from the beginning. So first of all, there's questions that are raised right away about whether perturbative renormalization is a mathematically sound method, about whether QED is indeed even a consistent, mathematically consistent theory. And what people are really interested in is, are there physical sources for the divergences, the infinities that arise when you do the calculations? And if so, can you put can you identify what they are in a clearer way than you were able to do just from looking at the perturbative formalism? So what I want to take a few minutes to do is to talk about a very early result that came in the foundations of quantum field theory program. And it's a result by mathematical physicist Rudolf Haag, proposed, initially formulated as a sort of informally proven conjecture by Rudolf Haag, so it's called Haag's theorem, and then proven a couple of years later, who was interested in this set of foundational questions, and specifically questions about whether the set of assumptions that's made in the course of representing interactions in quantum field theory, exemplified by QED and the other techniques that were on the table at the time, very early in 1955, were those sets of assumptions consistent? And second, how to think physically, how to think foundationally about renormalization and regularization. Are they necessary in any quantum field theory? Certainly were not necessary in non-relativistic quantum mechanics, and if so, why? Okay. So I don't expect you to read what's on the left, although you get a very big projection, so you can. I can talk about it on the next slide. But Haag's theorem is in the family of no-go results, which, of course, we all know and love Bell's theorem and find it very useful in foundations of quantum theory. So Haag's theorem is a no-go theorem like that. What Haag's theorem demonstrates is that if you take a certain set of theoretical postulates, which were presupposed in the interaction, picture that you find to use to represent interactions in quantum field theory, then you can prove mathematically that if that set of assumptions is consistently applied, then there's in fact no interaction. So this, of course, undermines the interaction picture. Okay, so here's how it goes. So what I'm presenting here is the version of the theorem that was proven just a couple of years later by Hall and Whiteman, using the Whiteman formalism, if you're familiar with that for quantum field theory. So this is a two-part result. The first part is not where we get the interesting part. It's just looking at spatial rotations and translations. What all you need to assume is that you have equal time canonical commutation relations. You assume Euclidean covariance, so this is just for the spatial degrees of freedom. You assume, so this is not Euclidean field theory, is what I'm saying. So then you also assume that you have special privileged states, which are going to turn out to be your vacuum states, which you definitely want to be invariant under these Euclidean transformations. And then you assume, in addition to that, for the purpose of the interaction picture, that if you have two sets of such fields, one representing the one set of free fields and one set of interacting fields, you want them to be unitarily related at some time so that you can represent your interacting fields using the free fields, which is the key trick of the interaction picture, of course. So then this just tells you that, if you assume that, then your V, which you're assuming is the unitary relationship between the two sets of fields, is going to be intertwined by the Euclidean unitary, and then you're going to end up with the vacuums being related by the unitary as well. So here's where the interesting stuff happens. So when we, in addition to the assumptions of part one of the theorem, we also take on board relativity theory. We also take on board Poincare covariance of the fields, Poincare invariance of these vacuum states. We assume that no states of negative energy exist. We want this to be a physical theory. Then you can prove rigorously that the first four Whiteman functions, first four vacuum expectation values are equal. So this is a general case where the two fields can be any fields. For example, two fields representing different interactions. In the special case where you are picking a free field as one of your two fields, then actually you can show that they're all equal. So that's not going to be there's not going to be a loophole like that. Okay, so what the upshot of this is it's telling you that the physical content of the two theories is going to be equal. So one slogan for this result is, if you represent interactions using the interaction picture, then indeed there are no interactions because everything just turns out to be the free field theory. Okay, so how to respond to this theorem? So I'm going back now a ways to tell you about the perspective from 1957, say, and of course you know what happened after, probably. But of course we can't accept the conclusion, right? We can't accept the conclusion because we want to represent interactions. It's not interesting to just represent free fields. We need to find a mathematical framework for quantum field theory in which we can represent interactions. Okay, so there's two ways of going here, which are going to be coming up throughout the week in a modern variance. This is a rough description of the historical variance, but the first thing you can do is stick to the physical principles that you assumed to set out the interaction picture, and then introduce renormalization and regularization techniques. Okay, so you can stick with the assumption that you're working with an interaction picture in which you have interacting fields that are unitarily equivalent to the free field, unitarily related to the free fields, but you need to introduce renormalization and regularization techniques in order to deal with the divergences that arise when you make that set of assumptions. The second thing you can do is of course, to axiomatize. And this is what Hogg famously did, and other mathematical physicists took seriously the idea that this result indicated a problem with the set of assumptions that you're starting with. It was a reductio result, no-go theorem. So what it tells you is that you need to reject at least one of the assumptions that goes into the result that you want to reject, right? So there's an obvious candidate here, right? The obvious candidate is the assumption that went in that you want your two sets of fields, the free and the interacting ones, to be unitarily related at some time. Okay, so there's unitarily inequivalent representations of the canonical commutation relations. This is acknowledging that they will be physically relevant, in this case, for representing different interactions. Okay, so we just pause here to emphasize that one of the things that's difficult about the RQI project is formulating QFT, and as you know, there's multiple different ways of formulating QFT that have been proposed that are on the table. So this is an early sort of diagnosis or indication of one reason why. So historically, this theorem conclusively shows that the mathematical framework for quantum mechanics cannot be straightforwardly carried over to quantum field theory. So there's already difficulties in challenges in formulating clearly what quantum field theory is as a theory. It's important to note, though, that Hogg's theorem already applies when there are only infrared divergences. So it doesn't really touch the more significant physical problem of UV divergences. So it's a relatively simple result from early days. So it only diagnoses one of the root causes of renormalization or regularization. My point in introducing it here is to just conceptually talk about the origins of the variety of different ways of formulating quantum field theory and where they come from. Okay, so the lesson I want you to take away here from the history of quantum field theory is that the unification of special relativity and quantum theory is a difficult project. I'm sure you knew that already. Maybe more interestingly, what makes it difficult, representing relativistic dynamics with interactions, as Hogg's theorem demonstrates, is the root of one of the difficulties. And so there's various ways of seeing this and also addressing the problem in renormalizing and regularizing, but then in the axiomatic program, thinking about other theorems that reveal other aspects of the tension, and then the ongoing program of constructing mathematical models for realistic interactions. Okay, so I should have put my picture back up here, but here's my picture. So I talked about, on the left there, RQFT, multiple ways of formulating it. Now I'm moving over to my question mark on the right, which is the measurement theory you want to put with it. So I know I don't need to say anything more to the people in this audience about why it's valuable to have a local measurement theory for quantum field theory, by which I mean a measurement theory which represents measurements as occurring to good approximation within local regions. This, of course, is contrary to the mainstream approach historically to representing and modeling measurements in QFT, beginning with QED, which is asymptotic scattering theory. Of course, we apply as an idealization. We never do experiments at plus or minus infinite time, but the model has that as an essential assumption in it. So there has been a long history going back to Bohr and Rosenfeld, if not earlier, of different approaches and proposals for modeling local measurements on QFT systems. And so I think it's useful and illuminating to see RQI as being a sort of contemporary development along these lines. And of course, one of the things that is a desiderata for a local measurement theory for QFT is that it must prohibit superluminal signaling by local measurements or local operations. For example, must block Sorkin-type impossible measurement scenarios. Okay, so the main point I wanted to make here is that this is not a new project either, and that, of course, this is something that there's been a lot of recent progress on, and I'm sure we're going to hear more about it as this conference goes on. Okay, so the two pieces I want to put together here, the dynamical theory and the measurement theory, both have a long history to them, which illustrates some of the reasons why RQI is embarking on a difficult research program. Okay, so now I want to turn to saying a few things which are in a more philosophical vein, in a more interpretive vein about quantum field theory. I want to talk about the measurement problem. So the is in quotation marks here. I'll talk about this more in the next slide, but the measurement problem is actually a set of cluster of related problems, not just one problem. But before I get into the setup of talking about what exactly I take the measurement problem to be, I just want to make a simple observation, which is that the problems I've just been talking about, the problems of how to formulate quantum field theory and how to formulate a local measurement theory for quantum field theory, are primarily problems for physics, how to formulate these theories. And the measurement problem is a problem that turns interpretations of the physics. So what I mean by this is, once you have the two pieces together, then the question is, how do we understand this as giving us either a description about the world, a description of the world and what's happening in the world, or else a description of how we as agents in the world who are trying to make our way in the world the best way we can, update our states of information about the world. So that's what I mean by interpretation. So really the measurement problem, and this is something I'll make more precise on the next slide, is a product, a result of putting these two pieces together. So the measurement problem we're all familiar with from non-relativistic quantum mechanics, it's a problem of a kind of mismatch between the theory, the dynamical theory, and the measurement theory that we put with it. So the main idea I want you to take away from this talk is that we've changed both of the ingredients that went into the measurement problem in non-relativistic quantum mechanics. So we switched from non-relativistic quantum mechanics to quantum field theory with a different way, relativistically appropriate way of representing the dynamics in particular. And we're adding to that local measurement theory. I take it there's not going to be a unique, as I've been saying, there's not going to be a unique answer about how to formulate the two, but whichever two you put together, they're both, whichever QFT you put together with whichever of the local measurement theory candidates you want to consider is going to be different in terms of ingredients than what we had in non-relativistic quantum mechanics. Okay, so the claim I'm making here is that the fact we've changed both of the ingredients is actually going to change the problem. So we're going to end up with a different measurement problem for quantum field theory than the one we all know. Well, philosophers have really thought about this a lot in particular, but the one we all know and is infamous for non-relativistic quantum mechanics. So I think just the fact we've changed the ingredients is a kind of plausibility argument for this claim. I have a lot more to say by way of argument that I can give in the next few minutes remaining, but I want to give you a sketch or more detail about what I have in mind here when I say the measurement problem is different for quantum field theory than the problem that we know from non-relativistic quantum mechanics. Okay, so the measurement problem is really a set of problems. Here's one problem in this set, which is at the core of the set, I think, and goes back to von Neumann as somebody who thought this particular problem was important. Here's a recent version of it by the philosopher Guido Bacigalupi from the Oxford Companion to Philosophy of Physics. So this is sort of an authoritative source of this particular problem. Okay, so this problem is that the practical rules of quantum mechanics, by which we mean the state update rules and the Born rule in quantum measurement theory, are not derivable from first principles by applying the theory, in particular the dynamics of the theory, as given by the deterministic Schrödinger equation to a measurement situation. Okay, so this is just the straightforward claim that you need to add the measurement theory on top of the dynamical theory. You can't derive it from the dynamical theory. Okay, so as I say, this is one problem. Another problem, important problem in the set of measurement problems, is what you might call the problem of the classical regime. This is what Guido does call it. So this is the problem of how we get a single classical measurement outcome recorded by our measuring device. Okay, so this is a separate problem. One way to think about this is that if you pick up a standard text in quantum measurement theory, this problem is specifically set aside for the purpose of presenting the measurement theory, state update rules. For example, Bush says, the subsequent processes of amplification and recording of the value of the probe observable into some macroscopic pointer observable is set aside, excluded, in order to avoid any interpretational commitment beyond the minimal interpretation. Okay. So the significance of the measurement problem in non-relativistic quantum mechanics is that it's an organizing principle for candidate interpretations of non-relativistic quantum mechanics, insofar as to have a satisfactory interpretation of quantum mechanics, you need to propose some way of solving the measurement problem as part of your interpretation. Okay, so there's two features of this problem that I've just been talking about. One is that the problem is really that you can't do the derivation because there's an incompatibility between the post-measurement state that's prescribed by the unitary dynamics, the Schrödinger dynamics, and the post-measurement state that's prescribed by whatever state update rule you want to use, selective state update rule. If you want to use Luder's collapse rule, for example, then you're going to have, but whichever one you choose, you're going to have a different state that's prescribed by the state update rule than you had from the unitary dynamics. And the second feature, which drives a lot of the interpretational work around the measurement problem, is that if you try to give a literal physical interpretation of the state update rules, then you might say, okay, the system follows the dynamics up to the point of the measurement, and then it follows what the state update rule says. And this gives you a measurement-induced collapse interpretation. So, for example, this is what Wigner gives us. He says, okay, clearly there's been a change, dynamical change in the state induced by the measurement at some point before a conscious observer comes on the scene, right? So there's some point at which the system collapses from a superposition into the state that's observed by our observer. Okay, so these are two characteristic features of the measurement problem as we find it non-relativistic quantum mechanics. What I want to say is that the situation changes with respect to both of these features when we move to thinking about quantum field theory. Okay, so first of all, by direct analogy to what I just had, the formal measurement problem in quantum field theory is that the practical rules of QFT, what we get from whatever measurement theory we pick, are not derivable from first principles by applying the theory, in particular the dynamics of the theory as given by the deterministic relativistic dynamics to a measurement situation. So again, that blue part is just the dynamical theory, which is the analog of non-relativistic quantum mechanics. Of course, one thing I've been stressing is that the situation in quantum field theory is such that there's multiple different formulations of quantum field theory on the table, and then now there's multiple different local measurement theories for quantum field theory. So you're going to have to pick some combination that fits together in order to formulate the problem. So here's what I want to claim, and I have arguments for this which go beyond the 5 minutes I have remaining. Okay, so my claim is that you can choose either algebraic QFT plus the FV measurement framework proposed by Fewster and Werk, or you can choose a combination of conventional QFT plus detector-based measurement theory proposed by, in this version, Jose Polo Gomez, Ray, and Martin Martinez. In either of those frameworks, you're going to find that the formal measurement problem I've just set up here has neither of the characteristic features of its counterpart for non-relativistic quantum mechanics. So you're not going to find an incompatibility between the post-measurement state prescribed by the dynamics and the post-measurement state prescribed by the state update rule. The state update rules are not going to be able to be interpreted in terms of admitted interpretation as literally physically representing a measurement-induced collapse. Okay, that there's not going to be a collapse that occurs upon measurement. Okay, so the claim then is that the problem is going to look quite different in quantum field theory once we've changed the ingredients that go into it than it did in non-relativistic quantum mechanics. Okay, so let me sum up what I have been talking about. So the first thing that I'd like you to take away is that history of quantum field theory can contribute to understanding why the much more recent RQI research program is a difficult project. So I think one thing you see when you look back at history is challenges that were faced, in particular representing relativistic dynamics in quantum theory. And secondly, the prior approaches that were taken to representing local measurements. And then I also want to leave you with the thought that relativistic quantum information may open up new possibilities for new interpretations of quantum field theory and its measurement theory. This is just what I'm talking about the measurement problem, that when you change the ingredients that go into it, then you change the problem. And when you change the problem, given that in quantum field theory, we're going to want an acceptable interpretation to propose some solution to the measurement problem, then since you've changed the problem, you're opening up space for novel interpretations of quantum field theory that are novel in the sense that they're not just straightforwardly carried over from non-relativistic quantum mechanics. All right, thank you.
Thank you very much. We have plenty of time for questions. I already see hands. Let's start from here. Nick.
Do I need a mic?
Yeah.
Do I need both mics?
Yeah.
Okay, I'm not sure which one to use. I think it's this one. Oh, this is recording. Got it. Okay, hi, I'm Nick Minicucci from RMIT University in Melbourne. I liked the presentation. I wonder why, I tend to think of quantum field theory as just regular quantum mechanics applied to quantum fields. So what is wrong with that way of looking at it? Because from that perspective, a quantum field is nothing but a collection of harmonic oscillators at every point in space. There's some continuum limit problems, and maybe that's where the trouble lies. But basically that's what you have, at least in my interpretation. So what is wrong with that? Where is the missing piece that doesn't let you just do that? Because if you did, you could just say, well, the measurement problem is the same in both cases. Thanks.
Okay, so I'm not sure the second part follows from the first, but take it the idea is that we shouldn't be so hasty to give up the framework of non-relativistic quantum mechanics. And instead of thinking of it as applying to particles or point particles or something like that, instead of applying the framework of non-relativistic, we apply the framework of non-relativistic quantum mechanics to fields, which have an infinite number of degrees of freedom and are spread out and et cetera. So, okay, so I think that that's one component of the switch, the change that gets made from moving from non-relativistic quantum mechanics to quantum field theory is the number of degrees of freedom, which of course is in some way partially responsible for the divergences that come out if you do the calculations in a way that's not sensitive to them. So one thing I want to stress though is that that's only one of the ingredients, right? And so I think this is the nice thing about what Hogg's theorem starts to show is that it's really it's not just the kinematics of the degrees of freedom that you're dealing with, it's also the dynamics, right? And so the shifting from Galilean dynamics to Poincaré symmetries is playing a big role here in that result, right? And so I think so one thing you might think is that in order to deal with the first problem, you're talking about simple harmonic oscillators or something like that, if you put everything on a lattice and put it in a big box, right, then you're reducing the field system to a finite number of degrees of freedom, but you're still going to have to renormalize, right? So you still might wonder physically why that is, right? So I think that one of the things that thinking about this sequence of results shows you is that the dynamics is also coming in to make things challenging. It's not just the kinematics of having an infinite number of degrees of freedom.
I saw a hand here.
Hi, so my question here is in your division which you have made, where would you put gravity if you would? Yeah.
Okay. So I started with this. I should have ended with it too. I didn't ever get to gravity, right? So this was really just thinking about the preliminary project of just taking special relativity, right? Just taking particle physics and trying to put it into the same kind of framework we're familiar with from quantum mechanics, where you have a dynamical theory plus you have a local measurement theory that you put on top of it. So in a way, obviously gravity would be the next project, and maybe one of the hopes would be that thinking about this more might help you. I'm not sure how that would go, but yeah, gravity doesn't fit on this page.
I saw another hand here.
Please.
Yeah, hi Doreen, very nice talk. But in terms of the first point up here, history of QFT, one of the things you didn't mention was this decoherence functional formalism of Gelman and Hartle, which back in the 90s was presented as the way of fixing all these problems. I'm guessing you think it doesn't. I'm wondering if you could comment how that fits in to this whole thing.
Okay, so decoherence.
Yeah, they had a decoherence functional formalism where you had a whole bunch of histories of possibilities, and you would just find the most likely one. And the way it was presented, at least as I recall, others may disagree, is that this resolved all of these kinds of issues in quantum physics. I personally never was satisfied with that, but I'm wondering what you thought.
Okay, so maybe I'll talk a little bit more about this slide. Okay, so the problem that I wanted to press about how it changes when you move from non-relativistic quantum mechanics to quantum field theory is a problem that has to do with how the dynamics play with the measurement theory, right? One of the things about this problem in non-relativistic quantum mechanics is not just the kind of problem you can solve with decoherence, right? So and this is maybe one way of thinking about how the different problems in this cluster of problems related to the measurement problem relate to one another. So the second problem, though, the problem of the classical regime, right? If you're thinking about how it is that classical physics, the physics that works for macroscopic size things emerges from quantum mechanics, then that's going to be where you might find decoherence playing a central role in the second kind of problem here, right? So maybe the diagnosis here is being more careful about what exactly the problem that you're trying to solve is, and decoherence is plausibly something that's going to be key to the second problem, but it's not going to help you with the first problem.
I saw a hand here.
Is this correctly? Does this work? Okay. The claim towards the end confuses me. For the Fewster Verge framework, I'm tempted to agree because it describes a measurement as scattering with a probe field, sort of leaving the question of actual statistics, scattering statistics, sort of at the side. But as far as I understand, the detector-based measurement theory essentially says we are coupling the fields to a non-relativistic probe, like a finite-dimensional quantum system, and then we are only measuring the probe in the usual way of non-relativistic quantum mechanics. And we are saying in the future light cone, there's the collapse, and outside there's just a pre-measurement, which averages over measurement outcomes. But my impression is that the detector-based measurement theory in that sense actually inherits all the parts of the measurement problem of non-relativistic quantum mechanics. So for that, I'm actually tempted to disagree with the claim, or at least I don't understand it.
Sorry, I missed the very last thing you said about what do you think helps with the problem for non-relativistic quantum mechanics? Here again.
So my impression is that the detector-based measurement theory actually inherits all the parts of the measurement problem of non-relativistic quantum mechanics,
Oh, I see. Okay.
since one is literally measuring a non-relativistic quantum probe. And all of the implications for the quantum field, like a collapse or something like that, come just from the entanglement with the probe.
Okay.
And at least because of the non-relativistic quantum system,
Just use the ordinary rules for state update from non-relativistic quantum mechanics for the induced observables that you have on your quantum field theory system. So it's true that you're using, in a careful way, the non-relativistic quantum mechanics model to model the probe, but you still end up with new state update rules, and it's the combination of new state update rules for relativistic theories plus QFT that I'm arguing gives you this new way of thinking about it.
Now, I have seen a number of hands, but we have used the time here. We need to postpone further questions to the coffee break.
I'm here all week as well.
Let us thank Corinne again. Could we have the next speaker set up?
Sorry, I'm just thinking beside you. Thanks. Okay, cool. Yeah, we need to talk more. Yeah, so yeah.
The weight of
quantum. Okay, good morning to everyone. I thank you very much, the organizer, to giving me the opportunity to present this experiment, actually. And this is an experiment that wants to make a measurement. And the measurement is performed in the isle of Sardinia in Italy. And I will show you why in a few minutes. No, I can you see it? Yeah. Posso fare? Come si fa a partire la presentazione? Okay, thank you. So this experiment is named Archimedes, and it is actually an interdisciplinary experiment, even if the main point is, of course, it is trying to measure the interaction of quantum fluctuations and gravity. Now, so the scientific motivation you know better than me. The key point here is to face the problem of having, let's say, a vacuum energy which is, let's say, much higher, whose effect is much lower than what is expected by applying the general relativity in a, let's say, ingenious way, in a straightforward way. So it is a very old problem. Now it is, I think, called the cosmological constant problem with all the derivation. So in our case, the key problem is to find an experiment that tries to measure if the quantum fluctuations do interact with gravity in the, let's say, usual way, what one expects, let me say, but their effect on the cosmological scale is cancelled by something else which is unknown, or, like some theories foreseen, the vacuum fluctuation doesn't interact with gravity in the straightforward way. So our starting point was the Casimir effect that I just recall. If you take two plates, two perfectly conductive plates, and you see that the quantum fluctuations inside the volume contained by the plates are lower with respect to the quantum fluctuation outside. And so inside the volume contained in the plates, there is a lower energy, even if it is infinite, of course, is a lower energy with respect to outside. This renormalized energy is called Casimir energy, which corresponds to a Casimir pressure among the plates. And this has been measured, has been predicted in 48, then it has been measured for the first time in the 50s, and now it is, let's say, considered acquired by the scientific community. Now, in our idea, what we want to do is to measure the vacuum fluctuations contained inside this cavity. So suppose to have a very, let's say, a rigid Casimir cavity. So we don't want to measure the force between the plates, but take the Casimir cavity rigid. And in this case, when you can consider when the plates are reflective, part of the vacuum is pushed away from the cavity. And so there is, if the vacuum waits, there is a force directed toward the height in the upper. This is, if you think for a moment, is an analogy with the Archimedes force. And this is why the experiment is called Archimedes. So we made this first calculation in 2002, 7, 8, and so on. And that's made, okay, this is acquired. But at a certain point, the first problem, in experimental problem, is to find a way to modulate the signal. I mean, here, the change of weight, the weight that we are talking about is very, very, very thin. So the first things that you have to take in mind that you cannot make a measurement we call indizi, or let me say, by just measuring a cavity with a balance. You have for the first things to make a way to modulate the signal. So this means to make the vacuum enter inside the cavity and go outside, enter inside and go outside, so that if you have a balance, you will have a signal which depends from the time. And in this case, you can take it, even if it is very thin. Now let me say that you have also to find a way, a very gentle way, to make this modulation, because again, the weight variation is very, very thin. So if you have in mind some too much heavy way of making this modulation, you will destroy the measurement you want to do. So in our case, the idea is to find a very gentle way to have this cavity whose plates are first, let me say, transparent, so that all the vacuum can go inside, and then make a trick to make the plates reflective, so that the vacuum is expelled from the cavity. The good way that we tried to do is by the use of superconductors. So imagine to have two plates that are made by superconductors. And if you slightly modulate the temperature, the superconductor makes the superconducting transition, and then becomes more reflective with respect to its normal state. So when the superconductor became superconducting. Sorry? Okay. So being a bit more reflective with respect to its normal state, the vacuum is pushed away. So as a first attempt, the first step, we just make a preliminary measurement to see if this is possible to make this such modulation. So these are results on a rigid cavity in which we see that if this cavity is, again, if the cavity has a superconductive plates, and the superconductors became superconductors, then you need, and you want to destroy the superconductivity by applying a magnetic field, then you see that when the superconductor is actually part of the Casimir cavity, you need a bit more of magnetic field to destroy the superconductivity, because its status is lower with respect to a normal superconductor, let's say to the superconductor which is not part of the cavity, because the Casimir energy is negative. So in order to perform back the transition, you need to give a bit more energy with respect to the case in which the superconductor is by itself. This is alone, let's say. So actually, this was good for us, a good hint for us, but it was not sufficient. It is too long to say this. So finally, we read this paper by Kempf, which is here. And he considered the same point, but in the stratified superconductors. And let me say, the idea of this behavior of superconductor, that it is very useful for us, because in this case, the distances between the plates that became superconductor, these distances are very small. So the Casimir effect is higher with respect to what we were considering as a starting point. So then, all in all, we decided actually to use this stratified superconductor for our experiment. And by making our calculation, of course, starting from the idea of Hakim, we found that it is possible to arrive to this force modulation on a real crystal, 5 to 10 to the minus 16 Newton, which is very teeny, but it is not prohibitive. So what is the measurement scheme in our case? In some sense, it's very simple, in the sense that you suspend two samples, two macroscopic samples, I mean a few 200 grams, more or less, to a balance, to an arm, and then you perform a transition, a superconducting transition of one sample and then the other sample. And you expect that the balance move like the arm of the balance move like that. Then to be very sensitive in this measurement, you have to, for example, to use another arm, which is a reference arm, in which is, if you are good enough, this is stable, does not move, the other one move, and then you make a measurement, a relative measurement of one arm with respect to the other arm. Okay, so this is an expected sensitivity. In this way, you can calculate the expected sensitivity and show that for 1 month of integration measurement, you modulate and you take data for 1 month. And you see that here the noise, this black curve is the noise. The noise can be lower with respect to a signal, for example, given at a certain period of modulation, let's say frequency. So let me say, if you look at this, you can imagine to modulate this transition with 100 second of time, I mean 10 to the minus 2 hertz, and take the measurement at this frequency, sorry. Now, I have to go fast. So this is what you have in mind. Then you have to make the experiment, which is difficult, I mean. What is needed to make an actual measurement? Now, we need an extremely sensitive cryogenic balance, which does not exist in the world at the moment that you want to do the experiment. Then you have to find a suitable modulation technique and a choice of the sample, a correct choice of the sample, and also find a very low noise place in which you perform the measurement, because otherwise the seismic noise will destroy your measurement. If you place this instrument in Naples, for example, for sure you will not be able to perform the measurement. So I will show you this prototype for two reasons. So the first is that you have also to provide a prototype to demonstrate that it's feasible and to be funded by the INFN, in this case, by the funding agency. And also, this is useful to show a bit how it works. So you have an arm that rotates around these very, very, very thin joints. Then these joints are loaded sustained by these pillars. And this is how it is the optical readout. So I don't enter in the scheme here. If you want, I can comment. But in this case, the key point is to find a simple scheme, but to preserve a very good sensitivity. So from an experimental point of view, as long as you are in simple, you gain, because clearly more is simple, the more it works. On the other case, if it is too simple, you are losing sensitivity. So in our opinion, this was a good scheme to maintain a very good sensitivity, which is interferometric, but in a, let me say, simple realization. So this is our prototype. We had also, I go on. These are the results of the prototype, which are in some sense good because we reached the thermal noise limit around this frequency region in which we wanted to do the measurement. This means that at least for what concerns the prototype, we cannot do better because we are really limited by a fundamental noise, which is the Brownian noise of the arm. And then, having this result, we had the money, and we, how much? So 10, okay. And we made the final apparatus. This is the cryostat, so which is quite big, as you see. And on the right, you have the picture of the present balance, which is almost ended. Let me say, for example, this apparently floating pieces, let me say, is a sample suspended to wires. The wires are very, very, very thin, so you cannot see. It is suspended to the arm, which is here. So the arm suspends one sample, which is this one, and another sample which falls inside this brown box, which is actually the box which changes slightly the temperature and modulates the status of the sample. And this is a picture, let me say, very, very, it's a usual picture of the commissioning activities, I mean, in which you find all that is not expected that make noise in the measurement. So we had also a very, very first measurement of the noise of our balance, of our final balance. let me say this is just to say that it is not that bad, because it is better than what we have mounted in Virgo, let me say. But if you wanted to joke a bit, this is an accident that we had. So this T here is a screw that when you move the screw, this is used to balance the arm, and it is balanced by the remote, because this fork here should move and make the screw going inside and outside. And in our case, we have this kind of accident in which the T went above the fork, so it is not anymore useful. So we had to reopen the vacuum. And okay, I will tell you, and this was an accident because we didn't talk to a very simple things, but I will tell you. I don't have the time to tell you. Now, also we choose the idea of modulate the Casimir energy by changing a bit the temperature of the superconductor inside this kind of oven. The superconductor, we use gadolinium BCO because its transition is very sharp. And then last things, we went in a very quiet site. The very quiet site is in Sardinia, in which there is no many anthropic activities, except for the ships. And this is good. I mean, this is good because really the noise is very low. But of course, it has the counter problem that this is not a real lab. I mean, we are inside an old mine, let me say. So this is in surface, but it is a building belonging to a mine, which is not anymore functioning. So we try to make it become a sort of laboratory, but it's very, very difficult, this job. Actually, there is the plan to build a real laboratory in the next future, but we have to move from our present laboratory to another one, to a temporary one. This is a temporary building in Orosei. So, before to conclude, I wanted just to stress that we had also the good point of having some fallouts of this experiment. The first of all is that we, let's say, help the candidature of the Einstein telescope in Italy by showing that this is actually a very, very good place where to perform a delicate measurement, as it is requested by the Einstein Telescope Gravitational Wave Observatory. Then, as a fallout, we have also the fact that when the balance is simplified, as we simplified, it is a very, very, very good tiltmeter. It takes the measurement of the position of the arm relative to the ground, and if the ground moves, if the beam is suspended and does not move, and the ground moves, then you measure the movement of the ground with respect to the beam, to the arm, which is stable. And actually, we succeed in having the best tiltmeter in the world in this region here, of few hertz, let me say, which is again useful for the gravitational waves observatories. Indeed, in fact, we installed such a tiltmeter in the Virgo gravitational wave observatories. And finally, another maybe interesting activity, which is at zero cost for us, is the direct search for ultralight by B-L dark photon. Now that we are really sensitive, this measurement has been taken with a prototype. Let me say that in our case, one night of measurement, which is this one, we almost reached the the limit taken by a microscope and similarly by earthwash. Okay, the key point here is that in case of microscope is 1 year of integration of time in the satellite. The kind of measurement is different. In the idea of microscope, for example, this is a so-called equivalent principle test. In our case, it's a sort of direct search, which means that you have a detector and you see if there is a signal of the dark matter in your detector. Okay, so to conclude, we hope that Archimedes will run, first we will run at room temperature in the next months until the end of the year. Then we have to move in the next lab, let's say, and hopefully we will perform the final measurement in the next 3-4 years. In our case, the main point is logistic, because to work in this condition, in this ISO, is not so easy. This means that there is a lot of effort to perform what you will do much better in a controlled lab. Okay, that's all. Thank you.
Thank you very much. We do have some time for questions, and I see ahead. Please wait for the microphone.
What is this for? For the streaming, yeah.
Ah, okay. So to microphone. Yes, thank you. Very, very interesting talk and impressive experimental effort. So I have 2 questions, remarks, slightly more theoretical, and I would like to hear your take on them. The first one is that there are some even paradoxes in relativity concerning the gravitation of pressure components that are resolved by realizing that sometimes it's important also to take into account the changes in pressure of an enclosing cavity when you have a fluid inside which has non-negligible effects of pressure as a source of gravity, for example. And so I was wondering whether in this case, the similar effect, the fact that you change the pressure of your vacuum inside, that will also have a counterpart in a slight change in the pressure of the cavity. And that might have also a sort of effect in the force experienced by that, and I'm not sure whether it counterbalance or what happens with that. So could you comment on that?
Okay, thank you. Very, very interesting question. It's too interesting to answer in a very, very short time. So, of course, when we change the, when we change the condition of the field, it should be correct to calculate the force not only considering the T00 component, but all the T mu component. No? This is what you say. And then let me say, there are arguments that in which you can say that, but we can talk, in which you can say that at the end, the effect of let's say the TEGA component is cancelled by the fact that you are in a closed system, which is in equilibrium. So it is cancelled by the TEJ of the matter. So what at the end you will measure is just the T00 because of the cancelling effect. This has been in any case a long discussion and papers favoring this point of view and in the other point of view. Okay? But at the moment we are thinking that it should be like that, let me say.
Okay, thank you. And just another remark. I think that it's definitely very interesting to look for a direct experimental measurement as you're proposing. But when you mention that we have no evidence, let's say, of that quantum vacuum gravitates, maybe it's interesting. There's some sort of theoretical argument saying that when you look actually at the radiative corrections to the energy of the nucleus, which is the main sort of inertial mass of the atoms, that there's a significant fraction that comes from loop corrections in QCD and so on, vacuum fluctuations, and then from very precise tests of universality of free fall, we see that it's actually gravitating as expected. So as I said, I think it doesn't say that it's very interesting to have a direct measurement as you are pursuing, but there are some hints, I would say, maybe, that quantum vacuum. Yeah.
Yes. Yes, you are also right. Let me comment on the fact that, yes, in this case, when you do an experiment, you have a controlled way to perform a real measurement. Of course, that's true that there are theoretical arguments in favor. Also, let me say theoretical arguments which are not in favor of that. Again, from one experimental point of view, this is a classical case in which to make an experiment is a good idea.
I agree. Thank you very much.
Up to one more question, if there is one. Okay, last question.
Hi, thanks for the talk. Now it's fine. So the first question is, I didn't really understand when you said that we let the vacuum enter and exit, like what are we doing exactly in the experiment to change the boundary conditions, or like
Yes. We change the boundary condition.
Okay.
The changing of the boundary condition is made by, suppose you have a cavity like that.
Okay.
This is, and suppose that this cavity is made by a first blue, let's say, material, which is a superconductor, and then you have a dielectric piece that just is used to make the cavity rigid, and then a second one, which is, for example, a gold plate, for example, which is completely reflective. Then the conditions are changed by making this blue plate becoming normal and superconductor.
Okay, so basically you make the plates effectively the plates perfectly conducting and not perfectly conducting some.
In some sense, yes. Of course, in an ideal way, it should be perfectly transparent and perfectly conductive.
But, okay.
We don't have this. We have a material which becomes a bit more reflective, and so the conditions are a bit changed.
But then, so I have the main question that I wanted to ask is that, so effectively the scenario becomes the same as essentially bringing the plates from infinity to a finite separation, effectively, right? And then if the scenario is physically this, essentially what we are doing is having a dynamical Casimir effect. So we know that if the boundary conditions are changing, you emit photons, right? Yeah. So how are we sure that the pressure that we are measuring in this experiment is not due to the photons emitted by the dynamical Casimir effect, and it's really the vacuum modes that are present in a rigid, ideal Casimir-like setup?
Okay. See, the fact that it is not dynamical is due to the fact that it is very slow. In time, it is very slow. So we are always in the, let's say, equilibrium condition. The fact that it is equivalent to have the cavity moved from infinity, this is also taken into account in many, let's say, calculation before us, by us, and it is acquired by the scientific community.
Thank you very much.
Thank you.
Could we have the next speaker come for a sit-up?
No, questo non lo fai.
C'è del filo, no?
Il ripeto? No, questi no.
E c'ha una sola entrata USB?
I'll give you signs to the 25 minute.
Very good.
Yeah.
Very good.
Yeah. You are right. The fact that
Si può scaricare questo sul desktop e poi si
the
mette.
Casimir energy, because it is big.
Sì, si
because
chiama
it is-
Napoli
There are many
2025.
modes.
Così si può togliere la
Also
chiavetta.
squeezing, you succeed in squeezing one mode typically. And so for our kind of measurement, it's too far.
Ecco, se lo può aprire e mettere in presentation. Sì. Ok, perfetto. Ora provo a mettere questo e vedere se funziona.
Oddio, scusa. Ce la fai a levarlo? Ah, ok.
The first speaker before the coffee break, Leonardo Castellani, Space and Time Correlations in Quantum Histories.
Good morning. First of all, I thank the organizers for the invitation and the warm atmosphere of the meeting. What I want to talk about today is something that was referred to by a colleague in the first row, the history formulation of quantum mechanics. There are many ways to speak about histories in quantum mechanics. Of course, the famous one is the Feynman path integral, and this will be a kind of generalization of that approach. And I will point out also some differences with previous approaches, like, for example, the Gell-Mann-Hartel or the Kotler-Wilczek approaches to this problem. The problem is simple, is to include in algebraic setting not only the state at a given time, but the whole history that develops from that time onwards, that is to include in the description of the state of a system the evolution and the instruments, the measuring instruments that you are using at each time to determine, via the results that you are acquiring, the states in which the system progressively collapses, okay? And this I will call a history. The sequence of measurement results will define what I mean by quantum history. But as an appetizer and also a motivation for this kind of description of quantum systems, I will recall an old example by Aronoff and collaborators, the quantum three-box game. And the ingredients are a quantum particle. You have three boxes, ABC, and you have measuring devices that are probing the system at 2 times, T1 and T2. You start at T0. At T0, the state is in a superposition of the 3 states ABC, where these mutually orthogonal states correspond to the particle being in box A, in box B, or in box C. Okay? They are eigenstates of the position of the particle. The first case that I want to consider is where in your lab you have only one measuring apparatus, that is apparatus that measures whether the particle is in the box A at time T1. Okay? Now you prepare the state at T0 in this state psi, and you post-select, that is, you these measuring apparati apparati are able to detect whether the particle is in A at time t1, and you have another measuring apparatus at time t2 that is able to detect whether the particle is in this state that looks like the state at t1 but has a minus sign. So this has to be the final state. Now, if you compute the conditional probability that the particle is in box A in the intermediate state, T1, and is in the state psi at T0 and phi at T2, you will find that the probability is 1. So there is a probability 1 of the particle conditioned to be at state psi at T0 and phi at T2. The probability, this conditional probability, is 1 if the particle is in state A at time T1. So that's an easy calculation you do with Born rule. Okay, but now notice that you could replace A with B, and the problem is totally symmetric in A and B. And so this means that the particle, if it starts in state psi and arrives in state phi at time t2, has also a probability 1 to be in box B. Okay? So this looks like a little paradox. It has probability 1 to be in A and probability 1 to be in B, because everything is symmetric in A and B. So what is going on? Well, what is going on is that we are making an assumption. The first case, we had a measuring device that could tell us whether the particle is in A at time t1. Now, in the second case, the symmetric case, we are not in the same physical setting, because now we have to have another measuring apparatus, not anymore the measuring device for the A box, but we have to have a measuring device for the B box. So you see, there are two different situations. We are changing the measuring device, and this is why there is an apparent paradox, but it is not a paradox because we are changing the physical setting. By physical setting, I intend also the one that includes the measuring apparatus. So measuring apparati are important in the description of a system, and this is one of the motivations of the history formalism I want to present. In fact, if you have, in another case, you have measuring devices that are able to detect in which box is the particle, so it means that you have a detector in box A, a detector in box B, a detector in box C, which is not the previous case. The previous case, you had only a detector in box A or only a detector in box B. Now you have detectors in all three boxes. Then you repeat the Born rule analysis, and you will find that you have exactly 1/3 of probability of finding the particle in intermediate time in box A, in box B, or in box C. Now, this is not unexpected. The evolution of a quantum system depends not only on his Hamiltonian, the unitary operator for time evolution, but also on which measurements you are performing on it at each time. So in this talk, we will propose a description for the time evolution that encodes not only the system data, that is the initial state and the Hamiltonian, but also the measuring apparatus that you are activating at each time. So this is a kind of motivation, and this is a short list of the topics I want to discuss. Probably I will not have time to discuss all of them. But examples will be taken from a very simple paradigmatic setting that is qubit circuits. The qubit is the simplest quantum system you can imagine, and just by putting some of them together, we will try to exemplify this history formalism. So, as I was saying, formalism that describes measurement sequences, histories are these sequences, and instead of a ket that describes the physical state at a given initial time, we will introduce a history vector that encodes both measurements and unitary time evolution. It is a kind of generalization of the Feynman path integral, and the probabilities will be obtained algebraically in exactly the same way we obtain them in ordinary quantum mechanics. I mean, this is not a new quantum mechanics. It's just traditional quantum mechanics put into a setting that may enhance and may enable to have a clearer view of how histories in the same quantum system are interconnected, entangled, disentangled, and so on. And the collapse will not be anymore a collapse of a single vector, a single ket, but a collapse of a whole history. Now, this history collapse, in fact, I want to motivate it a little bit further. If you think about simultaneity of collapse, which is something we are taking for granted, at least there is no evidence that it is reference dependent, the speed of collapse. And if you postulate that collapse is simultaneous in every reference frame, then you can take two reference frames, and you see that if Alice, the red line, is the word line of a qubit that Alice possesses, and the never works well. Okay, and the green line is the word line of Bob's qubit, and Bob and Alice share a Bell state, an entangled Bell state. Now, suppose that Bob makes a measurement in one of these reference frames, for example, the straight one, and then this is the simultaneity line for Alice and Bob, and you see that if Bob finds 0, then the state for Alice becomes 0. And this whole state, this entangled global state, collapses into this product state 0, 0. But the same happens in the blue reference frame. And in the blue reference frame, now this state becomes simultaneous with the qubit state 0 in the past of the qubit state 0 that we had in the straight frame. So this means that not only the state of Alice collapses at the time that is simultaneous with B in the straight frame, but also it collapses in the past of Alice, which means that if you insist on simultaneity of collapse, what you have to consider is the collapse not of a state, but of a whole history, in this case, the history of Alice state. So we have collapse of histories rather than collapse of states. Okay, this is the famous space-time approach by Feynman in his thesis work on path integrals. And now let's go to the specifics. Now, history, we said it is a sequence of measurement results. So what happens is the state, initial state evolves. This is the evolution operator from T0 to T1. And you measure it. You have a set of observables. Now, I consider to have at each instant of time a complete commuting set of observables that I call A1, and these alpha 1 are the eigenvalues of this complete commuting set of operators, and this is a shorthand notation for all of this. So alpha 1 are the results at time T1, and then the state alpha 1 evolves, and at time T2 you make measurements of another set of observables that I call A2, and I go on like this until time Tn. Okay, I'm discretizing time, but it is a simplifying assumption. Now, you can compute the amplitude for this sequence of results, and the amplitude is simply, this is defined via these operators U and the projectors on the eigen subspaces corresponding to the results. And this is the history amplitude. These P are just projectors, and they satisfy the projector properties. And the probability of the sequence of the results is simply given by the square root, by the modulus square of the amplitude. That's just repeated application of the Born rule. Now, the rules have this merging property, which comes immediately from their definition. And they satisfy to some rules that are due to the completeness of the projectors, the completeness property and the unitarity of U. If you sum on an intermediate alpha, then you get the amplitude where you don't measure anything at the time Ti. Okay, and this works for all these intermediate alpha, except for the last one, because the last one is just the ket, and you are not summing over that projector there. Now, the sum rules for probabilities for the moduli square of these amplitudes, well, they sum to 1, as probabilities should do, but the marginal rules are differing from the classical ones, because you have this marginal rule, which is the same as the classical probability if you sum on the last alpha n, but on intermediate alpha I, if you sum them, and you recall the definition of the probabilities as the moduli square, you will find that this is no longer true. This is no longer true, which is a marginal rule for classical probability. If you sum on intermediate results, classically here you have an equal sign, and classically you don't have it, and this means that this is a quantum signature of your system. But there are still probabilities. I mean, there are still the probabilities you compute with Born rule. So while a classical history is very easy to describe in its evolution, the quantum history is more like a Markov tree. At each time you have various possibilities, and for each of these possibilities, then the evolution gives you other possibilities and so on. Now, everything can be codified into a chain operator, which is this thing that is inside the amplitude, and it allows to express probabilities as trace of this product, and these traces, when they satisfy this property, then the histories are said to be decoherent, and this is the scheme that Gell-Mann and Hartel adopted, and it was taken from original work by Griffiths. And then you say that you have a consistent set of histories. When this happens, then the probabilities satisfy all the classical rules, and this is the reason why these people wanted to consider consistent histories. But this is not what I will do. I will consider all histories, even those for which this does not hold anymore, and I maintain that this is, in fact, the interesting case. It is the case when histories, like in the double slit, interfere with each other. So this is what we will do. Okay. Now, an example is the path integral, where, of course, histories do interfere with each other and give the amplitude of a process in the position configuration representation of the system. So here, these variable AI at each time are always the position operators in the case of the Feynman path integral, but now we are considering more general setting where the measuring apparati will not be only position operator. So this is the algebraic scheme I propose. I will introduce a kind of tensor product that I will call a time tensor product, indicated by this symbol here. And I will define a history vector space where you have a basis, and the bases are all the possible tensor products of these eigenvectors at each time. And I will postulate that this has all the properties of a tensor product, bilinearity and so on. Now, the general idea is that as subsystems of a composite system are described by tensor products, usual tensor products of ket vectors, now I can consider the same system, but at different times, and these will be the states at different times. And this I will call a temporal tensor product. This formalism will enable a symmetrical treatment of spatial and time correlations. Now, I will describe a quantum system with a history vector defined as a superposition of these basis vectors, and the coefficients of the superposition will be the amplitude of the histories, right? This is a straightforward generalization of a ket vector at time t0 expanded into the eigenvectors of a set of commuting observables. And I will define a history projector in this natural way. And just by computing, it's a one-line computation, you will find that the probability is given by exactly the same formula of the Born rule that you are used to in ordinary quantum mechanics, but now for history vectors and history projector. You have a history vector collapse after you make a measurement. And this projected vector you can use to compute conditional probabilities. It enables a graphical representation of the history vector that displays all histories with non-vanishing amplitudes. I just need two gates, the Hadamard gate and the CNOT gate, to exemplify it. And you can amuse yourself by giving a graphical representation of histories in the it's somehow, it is in the same spirit of Feynman diagrams, but now for qubits rather than for particles. And you have various circuits in which you can see how histories interfere, recombine, open up new branches, and so on, according to which measurements you are doing at which time, like in the teleportation case and so on. Now, the three-box game can be examined exactly with this graphical representation, and it makes you understand clearly how the histories combine into giving these apparent paradoxical results. Now, you can define product and entangled history states. Now, I'm just redoing the algebra that you do in the usual formulation of quantum mechanics about product states and entanglement. And you can have entangled history states, and you can define a history density matrix. And thanks to this history density matrix, now what you can do is to take partial traces and find out by the entropy, the von Neumann entropy, you can find out which history states are entangled or not when you have composite systems, where now compositeness is the usual compositeness. And all of this you can do, it's rather straightforward, and you can apply it to these simple circuits to show that it works. I mean, it gives sensible results. And you can define this history entanglement entropy that characterizes the entanglement in time and in space of bipartite systems, for example. Now, the traces can be taken not only in a composite system, but also in a single system. You take traces now on Hilbert spaces that you have at each time. And if you can, this can be done, and it will describe statistics not anymore of an observer that is confined to a sub-part of a composite system, but to an observer that has access to the system only at given times, not at all times. So before you had an observer that was limited in space, now you have an observer that is limited in time, and the description of his history state arises from taking a partial trace, not anymore on space, but on time, on this new tensor product that I introduced. And you can do it, and you can, in this way, explore the time correlation in the evolution of a single system, not anymore of a composite system. Okay, and this defines you what I mean by temporal entanglement. But what I would like now, well, you can define a time entanglement entropy that measures this, yes. You can probe, you can look at what it gives you in simple circuits to see that it gives you sensible results. But what I wanted now to conclude my talk with is that this formalism enables you to model evolution of a dynamical quantum system with a system that is not evolving anymore. It is a static system. So it's easy for a classical system. If you have one particle that is moving in phase space, it will have states qi, pi at the various times ti, and you can simulate it, you can describe it with a set of n particles at the same time that are in these states qi, pi, that are the states in which the single particle would evolve in the usual phase space description. Now, this is not so easy for a quantum system. It really means to replace this history vector with a vector that describes a static system, but a composite system made of n parts. Instead of n times, you have n parts of a composite system. Can you do it? Well, there is a protocol that enables you to do it, even if you don't know the initial state of the system, and this is the protocol. You evolve the initial state, then it becomes this. You adjoin a twin system. You use a unitary gate to clone orthogonal states. Orthogonal states can be cloned. And you evolve the second system to time t2. All of this you can do in your lab. And by evolving this, you are reconstructing exactly the usual tensor product, replacing the temporal tensor product. And this enables you to reconstruct this state. And it allows you to investigate then the temporal characteristic of a quantum system, for example, temporal entanglement between states, by means of measurements that are much easier to do on a static composite system. And these are more easy to perform. So these are the conclusions. This history vector formalism is a generalization of what we know. It incorporates measuring devices. It permits a symmetrical treatment of space and time correlations, space and time partial traces of the density operator. And the similarity of time and space tensor products and algebraic properties enables you to map an evolving system into a static composite system.
Questions before we break for questions. Yes, please wait for the two microphones.
Okay. So, as you already pointed out by referring to the superdense...
Where is the talk? Okay.
As you already pointed out by referring to the superdensity matrices of Jordan-Kotler, there are many formalisms that go into a similar direction, like isoprocess matrices, for example, or Feynman clocks. And one particular one that I'm interested in here would be the Page-Wouters formalism, because the Page-Wouters formalism also has something that is explicitly related to as history states. And I was wondering, in your framework, time doesn't seem to get a separate Hilbert space. So do you think that you could describe quantum effects?
Can you repeat this last part formally? It doesn't seem
Because of the like you have these history amplitudes that explicit.
I have these. Sorry.
Okay, you have the history amplitudes that explicitly model essentially a history as a succession of operators.
Yes, the amplitude depends on the measurements, on what you are measuring at each time, yes.
Do you think you could put in effects like redshift or maybe some, some control system?
Can you repeat? I cannot hear because there is some kind of reverberation in the room.
The acoustics of the room is regrettably not conducive to having the discussion out in full here. In the interest of time, may I suggest that we postpone the question to the coffee break. We'll start the coffee break now. We shall be back at 10 minutes past 11. Let us thank the speaker.
Thank you.
Does someone know how to turn on the screen?
So, Alex. Of this moment. Is the sound working?
I would say not that great.
Is the sound working?
Eduardo? Oh, okay.
So, advice for the speakers, we should apparently be quite close to the microphone when we speak. So with that notice, let us get going with the second half of this morning's session. At first, we have an administrative announcement from Haris Anastopoulos, the chair of the COST Action, which is a major financial supporter of this meeting.
Thank you. I'm not going. Oh, okay. No.
That's not working. Take
Okay.
Take them off.
Okay.
I think it's just on.
Okay, somehow. So, I'm just gonna take 1 or 2 minutes of your time. Our action is
Close to your mouth.
RQI as the relativistic quantum information and CA23.
Haris.
Yorma, the mic is not actually working.
And this is the code of the action. So this is the title of the action. This is the code of the action. If you Google it, you will find the web page. So the reason I'm telling you is that those of you that have not registered in the action, I would recommend that you do it during these days. And if you do it, please also sign the document that is outside about people that are present, because this determines the local organizer support that we are giving. So joining the action has some benefits. I can explain them I'm not going to take much time. We're going to have 6 or 7 conferences, 3 summer schools in the next 3 years. So that's all. Thank you. Can continue. Okay.
Thank you very much. So how is it on at all?
It's not going to work. You need to turn the volume up. It was working before.
So Alessio, any advice on the sound?
Turn the volume. Now we're gonna scan
Okay, so what are our options? To proceed like this or to wait? There is a lunch that we should make. Okay.
Does it sound good to you?
Okay, do that. Just hold that.
For the introductions, I will just shout, okay? So the first speaker in this session between now and lunch is Emily Adlam, and we see the title here, Is There Causation in Fundamental Physics?
All right. Hello, everyone. Thank you for the invitation. I'm very glad to be here. I did my PhD in RQI, and I am nowadays a philosopher of physics, so I'm very happy to come back and talk a little bit about some of the intersections between those fields. So yeah, the topic I want to talk about is this sort of ongoing philosophical discussion about whether there is causation in fundamental physics. And the reason I want to talk about that is because I think this is not just a philosophical debate. This has very interesting implications for various ongoing work in theoretical physics and for the way we should think about the physics that we're doing. More than 100 years ago now, Russell famously argued that there is no causation in science. As he memorably puts it, causation is a relic of a bygone age, surviving like the monarchy only because it is erroneously supposed to do no harm. Now, nowadays, I think people feel that Russell's argument is perhaps a little bit strong. We generally recognize that in areas of science when we're interested in sort of studying the ways in which humans can intervene on things and make changes, causation is a useful concept to kind of characterize those kinds of ideas. But nonetheless, many philosophers still feel that there is no causation in sort of fundamental physics, that causation is something that appears in other regimes, that is very useful to describe sort of human-oriented things, but it's not part of the fundamental fabric of the world. So that's the topic I want to discuss today. To what extent should we think there is causal structure in sort of fundamental physics itself? Now, as a matter of fact, I think Russell is sort of partly right and partly wrong here. So I'm going to start by explaining why he's right and why he's also wrong. And then I'm going to look at an example in the form of the process matrix formalism and try to understand what we might learn from that about the kinds of structure that we do have in fundamental physics. Finally, I'll talk about a couple of applications and methodological lessons. Okay, so just some sort of general comments about the concept of causation. First off, when we talk about causation, we're sometimes talking about relationships between general classes of things. So smoking as a general class causes cancer as a general class. Or sometimes we're talking about connections between individual events. So falling down the stairs was the cause of me breaking my leg. Hopefully those things are only going to happen once. So I'll mostly be talking about that latter kind of causation in this talk because that's often what we're most concerned about when we're discussing causation in physics and particularly fundamental physics. What else do we mean by causation? Well, one important feature of our notion of causation is that it's supposed to be something more than just correlation. There's this common mantra, correlation is not causation, so something else is needed on top of the correlation. What else is involved? Well, probably something to do with counterfactuals, right? One important feature of our concept of causation is that it kind of supports counterfactual assertions. If X is the cause of Y, then we normally think it's correct to say something like, if X hadn't occurred, Y would not have occurred, or it would have occurred in a different way. So that's kind of one sense in which causation is stronger than just correlation. We don't typically think that pure correlations support that kind of counterfactual reasoning, but we do think that causation supports that kind of counterfactual reasoning. Finally, a particularly important aspect of the common sense notion of causation is that it's asymmetric. If X is the cause of Y, then we would not normally think that Y is the cause of X. Causes and effects are supposed to be sort of distinct. And indeed, many philosophers, including Frisch here, have sort of argued that the asymmetry is really important and central to our notion of causation. So with that in mind, it's quite straightforward to see why Russell and other philosophers might feel that there is no causation in fundamental physics. Perhaps the main reason is because there doesn't seem to be very much asymmetry in fundamental physics. The laws of nature are, by and large, invariant under time reversal, as far as we understand, and that makes it hard to see how there could possibly be any kind of sort of asymmetric structure like causal structure is supposed to be inherent to fundamental physics itself. It has been argued that CP violations may be some kind of exception to that. I'm not completely sure that this is an exception. It depends on how you sort of interpret the time reversal transformation. But even if you do count that as a kind of temporal asymmetry, it's not really sort of widespread enough to change the sort of overall conclusion that, by and large, there doesn't seem to be much temporal asymmetry in fundamental physics, and so there doesn't seem to be much evidence of what we would normally think of as causal structure. Now, of course, there are many asymmetries in the macroscopic world. Those are the asymmetries that are usually involved when we talk about the asymmetry of causation. And most of those asymmetries seem to have something to do with thermodynamics, the sort of second law of thermodynamics, underlying various kinds of asymmetries, such as the fact that glasses often break and very seldom reconstitute themselves. And it's reasonably well recognized that the second law of thermodynamics probably can't be derived from microscopic physics alone. Something else must be added to get out those asymmetries. Commonly what we add is what's known as the past hypothesis, which is an assumption about the initial state of the universe. Roughly speaking, it's the assumption that the initial state was a state of very low entropy or something like that. The important thing for us here is that the past hypothesis explains why we get temporal asymmetries when we average over large numbers of particles, but it doesn't change the fact that everything is going to look temporally symmetric at a sort of fine-grained level. We only get these asymmetries arising at a more coarse-grained level when we do this averaging. So what we see here is a kind of picture where it seems to make sense to say there's nothing asymmetric and hence nothing causal in fundamental physics. Causation as a phenomena is something that emerges at larger scales when we get these kind of thermodynamic effects that give rise to the causal asymmetries that are so closely tied to our notion of causation. This is also related to a common philosophical analysis of causation. So one particularly popular way of thinking about causation is to relate it to the concept of intervention. Interventionist analyses of causation say something like, what it is to say that X causes Y is to say that Y would change if X were manipulated by an agent in an appropriate way. You can see from this definition that the interventionist approach to causation has the consequence that the facts about the direction of causation are going to end up being very closely tied to the facts about what agents can intervene on and what kinds of interventions they can make. In the kind of case above, we would normally expect that if I can change Y by intervening on X, then I can't also change X by intervening on Y. There's some kind of restriction on what kinds of intervention I can make that gives sense to this notion of an asymmetry. And so because all those facts about interventions are to do with thermodynamics and also to do with our sort of nature as embodied observers and the restrictions that imposes on us, this again seems to support a picture where causation is not there in fundamental physics. It's something which appears at higher scales where you have observers intervening on things and you have various restrictions on the interventions they can make. Intervention is also often linked to the causal modeling formalism, which is one way of thinking about the nature of causation a bit more quantitatively. So a causal model is a directed acyclic graph whose edges represent causal relationships between the variables, together with some conditional probabilities describing the conditional probabilities for one variable conditional on parents in the graph. So the causal modeling is a very natural fit with an interventionist approach to causation because a causal model is a nice way to determine quantitatively the results of various possible interventions that agents could make. We just kind of imagine changing the value of one node in our graph and look at the consequences for other nodes in the graph. The key point for us here is that if you're trying to infer a causal model from some correlations, you're not generally going to be able to do that in a sort of unique way based just on a set of correlations alone. Typically, to infer anything about causation, you have to start by identifying some of your variables which you're going to treat as exogenous variables, meaning that they have no parents in the graph. So they're the source of causal influences, but they are not influenced by anything in the graph. And so you have to therefore have some way of deciding which variables are going to count as a natural way to do that. We commonly identify the exogenous variables as the ones on which humans do intervene or could intervene, with the thought being that the intervention kind of cuts the variable off from any previous causal influences on it and allows us to treat it as a kind of external source of information. So again, interventionism and causal modeling here seems to support a view where causation is quite macroscopic in character and relies on the presence of observers who can perform interventions. Now, of course, you might say it is possible for us to intervene on the microscopic world too. We can do laboratory experiments, we can make things happen microscopically as well. And I think it's fair to say that in those kinds of cases, there is a derivative sense in which it does make sense to use a causal description. I turn on the particle source here in the macroscopic world, and microscopically that causes the particle to pass through the slit. But I think when we're using that kind of talk, we shouldn't forget that the direction of that description comes from the macroscopic world rather than from the microscopic description. What I'm doing there when I give that causal description is, in effect, sort of translating the causal asymmetry of the macroscopic world into the microscopic world for the purpose of giving a description. That asymmetry probably is not present in the sort of intrinsic structure of the microscopic physics. It comes from the macroscopic world and the asymmetries we have there. So that's not to say we shouldn't use this kind of talk, but just that we should perhaps be aware that we're importing some features from the macroscopic world into the microscopic world when we do that. So for all of those reasons, I think Russell is to some extent right to say that there isn't such a thing as causation in the ordinary sense in fundamental physics. Certainly, there doesn't seem to be much scope for there to be asymmetric causal structures in the way we would normally imagine. You're not going to get anything that looks like a directed acyclic graph out of just the structure of the microscopic physics. On the other hand, I also think there are some reasons to think this conclusion is maybe a bit too quick or needs to be moderated. So one of those reasons is that physicists do seem to use causal language all over the place in their descriptions of the microscopic world, and they do that even when nobody is intervening on it. We often sort of tell causal stories about things like the early universe, for example, when there was nobody around to make interventions. And that kind of talk seems to be relying on some kind of structure which doesn't require macroscopic interventions and macroscopic asymmetry. Now, perhaps Russell and supporters might be tempted to say this kind of talk is just nonsense and doesn't make sense, but I think that really can't be right. This kind of talk is often useful and productive. It does seem to be sort of characterizing some meaningful structure that is really there in the physics, and so I think it would be a bit unreasonable to say none of this makes any sense. Moreover, even if we don't think the microscopic world has causal structure, for sure the microscopic world has some kind of structure that is intrinsic to it. If you imagine a scenario in which a particle decays and releases a photon, and that photon is later absorbed by another particle. Since nothing macroscopic is going on here, I can presumably describe all of this in a sort of time-reversible, symmetric way. So in some sense, there's no causation present here because there's no asymmetry. But nonetheless, there's surely some kind of quite robust connection between the decay and the absorption. That's not just a correlation, there's something a bit stronger going on there. And we can sort of see that there's something stronger than correlation going on there by the fact that certain kinds of counterfactual assertions seem appropriate here. I would be tempted to assent to the counterfactual if the particle had not decayed in this specific way, the photon would not have been absorbed in this specific way. And maybe also to the reverse counterfactual, if the photon had not been absorbed in this specific way, the particle would not have decayed or would have decayed in a different way. So because what's going on here does seem to sort of justify various kinds of counterfactual assertions, that makes me think that there is something, some kind of structure here which is sort of similar to causation in the sense that it is stronger than a correlation and it supports counterfactual assertions. So what that sort of suggests is that even though there might not be causal structure in the ordinary sense present in fundamental physics, there is some other kind of related structure, and it seems like a useful task for both philosophers and physicists to think about what that kind of structure that is and what kind of reasoning that supports. So to think about what kind of structure that might be, I think it's very helpful to have a look at some recent work in the process matrix formalism. The process matrix formalism has been developed for reasons that have nothing to do with the philosophy of causation, but I do think that sort of on the side it has some really interesting consequences for how we should think about causation, and so I'm going to go through and try to explain what I think it tells us about the nature of causation in the physical world. So the process matrix formalism is basically setting out to try to circumscribe the most general possible class of processes you could get if you don't place any restrictions in terms of the embedding in space-time, the causal relationships between them, or anything like that. So basically, the setup is going to be, we imagine that we have a set of laboratories. Within those laboratories, we're going to follow the usual laws of quantum mechanics, but we're not going to place any particular restrictions on where those laboratories are in space-time or whether they are in a space-time at all. We're not going to demand any particular kind of preset causal structure or temporal structure. We're going to allow basically any kinds of connections between these laboratories. So the only kind of restriction we're going to put on these laboratories is that we require that the process, whatever it is, shouldn't produce logical contradictions. So to see what I mean by that, we can consider this process depicted here. So in this process, we imagine that my past self, Emily 1, receives a bit value B. She puts that bit value into a process P1, which produces an output somewhere in the future. Let's just say the output is equal to the input. My future self, Emily 2, takes that bit out, gets that output, flips the value of the bit, and then uses that as the input to a new process, P2. That's going to be oriented in the opposite direction. So my past self, Emily 1, gets the output from that process just in time to use it as the input to the original process, P1. And as you can see from the diagram, this seems to lead to a significant problem. It looks as though this bit value B needs to have two different values at the same time. It needs to be both 0 and 1 simultaneously. And so assuming we're not going to allow any kind of like multiverse situation here, that seems like it is a contradiction and it could not possibly happen. So something has to be done to prevent that. So we shouldn't allow processes like this or compositions like this. We should forbid this kind of contradiction. So that's basically what the process matrix formalism is doing. It's seeking to encode the most general class of possible dynamics on a set of laboratories, subject only to the restriction that they should guarantee the absence of contradictions like the one on the previous slide. So we're not going to assume global temporal order or causal order or anything like that. We're just going to rule out contradictions. Formally speaking, we can do that using a process.
Can I try something? Could you keep this apart from that?
Okay. Formally speaking, better? Formally speaking, we can do this using what's called a process matrix. A process matrix is a higher order map. Sorry.
You can put it like this. Oh, sorry. Sorry.
Yes, does that work? Yeah, okay, great. A process matrix is a higher order map from a set of quantum operations to another operation. So what it does is it takes the set of operations performed by the agents in the individual laboratories to another quantum operation, which represents the net effect of performing all of these operations in the context of this particular process. And we can use a mathematical condition on the process matrix to ensure that we have ruled out contradictions like the one I've described. So within the process matrix formalism, we can define various different classes of process matrices with different quasi-causal properties. The causally ordered ones are the ones compatible with the existence of a strict partial order with outcomes in some laboratory depending only on earlier settings. So those are kind of similar to the familiar types of processes we know where things occur in a well-defined order. Causally separable and causal are both slight generalizations of that, which make things a bit more free, but still sort of maintain the idea that there's a well-defined order. And then we also have a few non-causal processes, which are processes where you can't put the events in some well-defined order. That involves things such as processes that go around in a loop, perhaps the kinds of processes you might expect to see on something like a closed time-like curve. No processes like that have yet been observed in reality, but it is very interesting to note that it's possible to define processes which go around on a loop like that and which nonetheless guarantee the absence of any contradictions like the one that I've shown. Okay, so looking at the process matrix formalism, what I want to do now is to try to define the kind of structure that we have that is instantiated by causally ordered, causally separable, and causal processes. I'm going to call this type of structure causal order, and so we can say that a set of laboratories belonging to a process exhibits causal order if and only if there exists at least one choice of strict partial order for these laboratories which is compatible with the signal requirement, and there exists at least one choice of strict partial order which is not compatible with the signal requirement. So here the signal requirement is just the idea that for any possible choice of local operations, the outcomes obtained in each laboratory should depend only on the settings in that laboratory or in laboratories earlier in the process. So it's just the idea that signals should be passed sort of linearly through the process. And by imposing the signal requirement, we can sort of extract a specific kind of structure which is inherent to the process itself. So you can sort of see from this definition, there are two ways to fail to exhibit causal order. One way is that no possible order is compatible with the signal requirement. That's what we get with the non-causal processes. The other way is because all possible orders are compatible with the signal requirement, and that in particular occurs with processes that just aren't signaling, because if you're not sending signals, then you sort of can't fail to obey the signal requirement. So there are those types of processes that don't exhibit causal order, but for all other processes, what we find is that imposing the signal requirement kind of picks out a natural order that's associated with the definition of the process itself. It's part of what the process is. It's not coming from any sort of separate temporal order or space-time structure. It's right there in the definition of the process. So a process that exhibits causal order can be thought of as having a sort of inherent ordered structure, which is independent of time, space-time, and so on. It's really there in the definition of the process. And looking back at the definitions of causally ordered, causally separable, and causal as they're used in the process matrix formalism, you can sort of clearly see that the word causal here is referring to what I have called causal order, and not necessarily to anything stronger or similar to our common sense notion of causation. So we know from the process matrix formalism that many processes in nature, including in fundamental physics, exhibit what I've called causal order. And because the word causal is in the name of that, you might be tempted to say, well, that looks like a counterexample to the claim that there is no causation in fundamental physics. But that, I think, is a little bit too quick. Since the main sticking point for having causation in fundamental physics was the absence of any asymmetry, we should go and ask, does this type of structure, causal order, actually involve any kind of asymmetry? You might initially be tempted to think it does involve some asymmetry because it's called an order, and when we think about orders, we often think about them as going in some direction from the beginning of the order to the end of the order. But if we go and look at examples of causally ordered structures, we can see that, as a matter of fact, this kind of ordered structure does not require any asymmetry. So for example, PNR has shown that certain kinds of process matrices are causally reversible. What that means, in effect, is that if you take a process which exhibits some causal order, and then you reverse all of the arrows and you rename the inputs as outputs, the result of that is often going to be another process which also exhibits causal order in the opposite direction. So in that sense, we have a sort of intrinsic ordered structure in this kind of process, but that intrinsic structure does not require that there's any asymmetry or direction to the process. We have a sort of ordered structure that we could equally well describe in either direction. What matters is not the direction, but the sort of well-defined order within the process. So this, I think, demonstrates that causal order, despite the name, is not, in fact, intrinsically asymmetric, and therefore it's a kind of structure that can be present in fundamental physics, even if there is no temporal asymmetry in fundamental physics. I find it helpful here to distinguish between asymmetry and order. The example I like to give is of a ladder, which is like symmetric around the horizontal axis. So that ladder has no intrinsic asymmetry. The top is not different from the bottom. But nonetheless, if you start going up the ladder, you'll encounter the rungs in some well-defined order. If you start from the other end, you'll also encounter the rungs in some well-defined order. So the structure that really matters there is the sort of well-defined order, which is in some sense the same in both directions. Those are just two different choices about how to describe it. I sometimes call this a bi-order, by which I mean like an equivalence class consisting of an order and the reversed order. That's intended to express the idea that there's some kind of an intrinsic order where the direction that you describe it in is just a choice of description. So the point here is that, at least in many contexts, causal order seems to be a bi-order rather than an order. It doesn't seem to require anything that's really intrinsically asymmetric. So in that sense, it doesn't seem to be causal in the sort of ordinary sense. It doesn't satisfy the asymmetry requirement, which is supposed to be an important aspect of our concept of causation. But nonetheless, it seems to be closely related to causation. And so it's a good candidate for a sort of structure which is there in fundamental physics, which plays a similar role to causation without actually being the same as causation in the ordinary sense. Indeed, causal order seems to be quite ubiquitous in fundamental physics, and we can sort of see why if we go back and look at the original motivations for the process matrix formalism. Recall that one of the main things we set out to do was to define these processes in a way that avoids logical contradictions. And causal order is a really natural way of avoiding that. If you can assign an order to the process such that things later in the process depend only on things earlier in the process, then kind of by default, you can't possibly get the kinds of contradictions that I showed earlier. So processes instantiating this kind of causation are sort of automatically self-consistent and don't run into those kinds of problems. I sort of like to think of causal order as something like causation without the asymmetry. In particular, one thing I'd highlight about it is that it's still associated with counterfactuals, right? That's because the definition of a process is about not just what actually happens, but also includes information about what would have happened if you chose different inputs. And therefore, causal order is a statement not just about actual happenings, but also about various counterfactual happenings. And in that sense, it is still stronger than correlations. It's still able to support the kind of counterfactual reasoning that we like to do when we talk about causation. Final thing to note about it is that if you take a causal order and you choose a direction through it, the result of that is going to be a directed acyclic graph, exactly the kind of graph that we like to use to model causation in the causal modeling formalism. So this, I think, suggests quite a nice story about the origins of causation in the macroscopic world and the nature of that structure. We can sort of see that the causal order itself comes from the underlying microscopic physics, and meanwhile the direction comes from macroscopic considerations like thermodynamics, our nature as embodied agents, and so on. So you put together the causal order and the direction, and what you have is a directed acyclic graph, which represents the kind of causal structure that we're familiar with in the macroscopic world. So I think sort of both of those things are needed to explain why we get this kind of causal structure in the macroscopic world, and to tell us about how that kind of structure is related to microscopic physics. Okay, I want to finish by talking about a couple of applications and methodological conclusions we might draw from this line of reasoning. So one important application is going to be to the way that we think about non-locality. Causation is a pretty important issue in our discussion of non-locality. Many of the worries that people have expressed about non-locality are to do with the difficulty of telling a sort of consistent and sensible causal story about these correlations. So it's interesting to see what happens when we try to apply the definition of causal order to non-locality. Something very interesting happens here because the definition of causal order, if you recall, was all about signaling. In particular, we saw that in order to exhibit causal order, we have to have the signal requirement placing some kind of non-trivial constraints on the process. And that is only going to happen if the process is sending signals. Processes that don't send signals will not have any kind of natural order emerging when we impose the signal requirement. What that means is if we try to impose the definition of causal order to something like a Bell experiment, precisely because there are no signals going from one laboratory to the other laboratory in that experiment, imposing the signal requirement won't impose any ordered structure, and so we won't get causal order between those laboratories. They're not going to stand in any kind of well-defined order. There's not going to be a natural ordering for them emerging out of the nature of the process. What that means is that if you think of causal structures as emerging from the combination of an underlying causal order plus a choice of direction, in a Bell experiment, there just is no causal structure relating those laboratories. We still have a direction, we have observers intervening on things, but we don't have an underlying causal order, and so there's no causal structure here that relates these two laboratories. There's an interesting result due to Wood and Spickens, which notes that any causal model which reproduces the Bell correlations must be fine-tuned. In light of what I said on the previous slide, I think that that's not at all surprising. This is a type of process that really does not instantiate causal structure. So sort of inevitably, when we try to force it into a causal form, we find that it looks sort of artificial and weird. That's because it is not causal, and therefore we probably shouldn't be trying to describe it as causal in that sense. There have been some attempts to generalize the concept of causation to address that, for example, within the quantum causal modeling formalism. This can certainly be very useful, particularly if we're trying to characterize sort of operational possibilities for what kinds of things we can achieve with non-locality. But I think we should be cautious here because in some cases, the right thing to do might not be to try to generalize the concept of causation, but rather to appreciate that this is not a causal phenomenon in the ordinary sense. That is also, I think, a useful lens through which to see non-locality, and so we shouldn't we shouldn't forget that although we might sometimes use causal terminology in this context, in some sense what's going on here is not a causal process in the ordinary sense. So finally, just a couple of thoughts about what sort of consequences this might have for methodology as we go on and try to do physics and to study the features of microscopic structures. First thought is that trying to impose a specifically causal structure on microscopic physics is not always going to be a good idea. Imposing a causal structure does make sense when our goal is to draw like an operational conclusion about what macroscopic objects like us could achieve in the lab. That's exactly what the concept of causation is really good for, so for sure it's fine to do that. But if our goal is not just to say operational things, but rather to understand the structure of the microscopic world itself as sort of separate from interventions that agents might make, then talking in causal terms may not always be the most useful thing to do. Certainly we should be cautious about understanding which of these two things we are trying to achieve in any given situation, and to think about whether causation is the right concept to use based on what we're trying to achieve. Relatedly, we're sort of seeing here that there are types of structure the world could have other than causal structure, so we don't always have to kind of advert to causal structure when we're trying to describe what's going on in the microscopic world. There are alternatives which might be more natural and more informative. If we appeal to something like causal order or other kinds of sort of more symmetric structures, we can still give descriptions of the structure of the microscopic world. We can still be realists about the microscopic world if we want to, without having to attribute causal structure to it. And indeed, perhaps thinking more generally about other types of structure that could be exhibited could be a useful way of making progress. For that reason, to prevent confusion, it might perhaps be a good idea to use the word causation a bit more sparingly, and to avoid using it if we're not really talking about causation in the standard everyday asymmetric sense, and rather to have some sort of other terminology to talk about other kinds of structure. Finally, because there is, as I see it, no asymmetric causal structure in microscopic physics, I'm wary of the idea that telling different kinds of causal stories can give us relevant insight into non-locality. And indeed, I think trying to sort of describe these things in causal terms can lead to unnecessary confusion. The same is very likely also true for other quantum phenomena that we're interested in understanding, such as contextuality. So I'd like to suggest that if we are going to use causal terminology in our discussions of these phenomena, we should try to be really clear about what the purpose of the terminology is, and in particular to specify clearly whether our use of the terminology is intended to be grounded in macroscopic or microscopic facts. So that's more or less it from me. Thank you very much for listening, and I guess we should see if there are any questions.
Now for the questions. Is the protocol that we pass the recording microphone to the speaker, to the person who asked the question? Other than that, we ask you to speak up. I saw one hand here. Nick.
Thank you. Thank you for the talk. I'm Nick Menicucci. So my question is, I like this idea of the ladder that can go either direction. Mm-hmm. And I've had thoughts along those lines, but nowhere near as developed as you have. So I'm wondering, is there some sort of dictionary that if you have some sort of protocol, like, I mean, a simple one would be emission of a photon from decay of an atom. Yeah. If you time reverse that, it would be absorption. Mm-hmm. But is there some sort of dictionary that can be provided for more complicated processes? Does such a thing exist in the literature?
Yeah, so I'm not aware of anything sort of fully general. The thing that I found was closest was PNR's work on like reversing process matrices. That's obviously designed specifically for the process matrix formalism, but like many things can be sort of written into that formalism. So that doesn't apply to everything, but that gives a recipe for reversing at least some kinds of processes if they can be put in that form.
Right, very cool. Thank you.
I saw one hand over here and then another one here.
Thank you. So I have a question about the Bell scenario.
Yeah.
The way I see it is that there's a common cause, which is the preparation of an entangled state,
Yeah.
which gives rise to the correlations that we observe. So why is that wrong in any sense?
Yeah, so I mean, what you have to do is to like track where the signals are going, and for sure there are signals from the preparation to the two experiments. So if you apply the notion of causal ordering to that, you will certainly find that there is a causal order relating the preparation and the two experiments. The claim there was just that there's not going to be any causal order relating the two experiments to each other because they're not a signaling process. For that reason, I think it's perfectly fine to use causal language to describe the sort of interventions that people make and that kind of thing, but we should be careful not to assume that the whole thing can be described in causal terms. I think the relationship between the two experiments just should not be described in causal terms.
Thank you.
I saw Rob's hand down here.
So yeah, hi Emily. So I mean, in the previous slide, like I take your points, but it seems to me that you're implicitly assuming that we know what the macroscopic world is and the micro world is, and when one begins and the other ends. Yes. But do we?
Yeah. So I mean, I guess the story I told about causation in the ordinary sense is that it emerges at sufficiently large scales as we average over things. So that, emergence is never an exact process, it's an approximate process. So I wouldn't expect there to be an exact boundary where you can say, here there is causation and here there is not causation. But certainly there are sort of obvious cases where things taking place in the ordinary everyday world are macroscopic and have a lot of asymmetries. Things taking place deep in fundamental physics tend to have very few asymmetries of that kind. So it's not sort of a strict, there's a strict border between them where we can and can't use causation, but just that we should be sort of aware to be careful about projecting more macroscopic ideas into the microscopic world.
Okay, fair enough, but it still seems to me there's a lot of stuff in there we don't understand. Would you agree?
Well, I don't take causation to be like an exact concept. I do take it to be something that sort of emerges in an approximate way. So for that reason, I wouldn't expect there to be exact clear lines about where it is and isn't.
No, but how it emerges needs to be understood, does it not?
Yes, and I think the story we have about the emergence of the second law of thermodynamics, for example, is getting there, but there are certainly many aspects both in philosophy and physics that need to be sort of further resolved and worked on. So for sure, the sort of emergent story has gaps in it that we'd like to fill.
Now, I see a number of hands. Let us take one more question, and I believe the earliest hand I saw was from Harris. Please wait for the microphone.
Yeah, there is a microphone.
And please speak up.
Okay. I understand that the key point is the time asymmetry, that there is no time asymmetry in fundamental physics.
Yes.
But out of the interpretations of quantum theory, at least half of the most popular ones are time asymmetric.
Yeah.
Many worlds, Copenhagen, the coherent histories. I mean, so the conclusion depends on the interpretation, right?
So I wouldn't say that many worlds is
It has branching. It has branching.
It's not asymmetric at the fundamental level. The branching is emergent, much like thermodynamics and causation. But yeah, certainly collapse interpretations do look like they're asymmetric at the fundamental level. So it's true that some of this is going to be dependent on your interpretation of quantum mechanics. I think I'm most concerned with cases where people are discussing often discussions of sort of unitary effects in quantum mechanics, where there don't seem to be any asymmetries, but people will still use causal language. And so I'm just wanting to sort of advocate some caution in the use of causal language when we're describing things in regimes where we're not postulating any asymmetries.
Right. Okay.
Let us thank Emily again.
You might need to give me a hand with this. It's harder to get on, I think. Oh, is that it?
Do you have HDMI? Or?
Oh yes, HDMI is on the other side. Oh no, just come off. Could you give me a little hand with this, because it's not... Is that actually on properly? No expertise. It's better. It doesn't feel better. All right, I'll try it. Okay.
Next speaker, Chris Fewster, Measurement and Preparation Protocols for Quantum Field Theory on Curved Spacetimes.
Well, thank you very much indeed. Thank you to the organisers for the invitation to be here. While I was listening to Emily's very lucid talk, I realised that my title may be alphabetically ordered, but it is not causally ordered. So was Russell okay with alphabetical order? He's okay with that. Good, right. So that's a good start. So because, of course, what we do when we're doing experiments is prepare first and measure later. And this is part of the story that I will tell, and I think this links nicely to Emily's talk. So I'm going to talk about a framework for measurement in quantum field theory that Doreen's already mentioned, and which I will describe in a little more detail. And this was developed with Rainer Ferch, and I'm going to describe some new material which is in preparation. We'll come to that in a little bit. So here are some fundamental issues, or issues I take to be fundamental, in both quantum field theory and in relativistic quantum information theory. There are several things we might like to do. We might like to transfer information from one quantum field theory to another, from electrons to photons, photons to electrons, and so on. Measurement, if you like. We also want to gain access to local observables. We want to gain access to any of them. We'd be happy maybe if we can do that approximately, but ideally we want to do it exactly. We also, in order to do our experiments, need to prepare states, at least locally. We don't care about the state at Alpha Centauri. We do care about what's happening in Sardinia. Well, Enrico certainly does. We also want other people to do experiments too. When we have the parallel sessions this afternoon, it certainly, we hope, will not matter what's going on in one room for the results of the talk in the other room. There must be the possibility to work independently at space-like separation. And we also need a clear understanding of how states should be updated consequent upon measurement or other operations. So what I'm going to do in the remaining time is try to explain how we can fulfill all of these needs within quantum field theory on curved spacetimes, and this will all be in the context of this measurement framework. So let's begin. So the basic idea is we wish to have a system quantum field theory that it will be called A, and a probe quantum field theory imaginatively called B, and these are on a globally hyperbolic space-time. If you don't like curved space-times, just think of Minkowski space, but I want to emphasize that everything I say can be done in general curved space-times. These two quantum field theories are going to be coupled together. That's the intervention that is being made by the experimenter who set something up in the lab. This creates a different quantum field theory from the one you first started of. It's got an interaction between these two types of field. And we're going to assume that that is a quantum field theory in its own right. And that is the crucial assumption of the whole framework. When you do that, you realize that you can encapsulate all the information about the coupling in a scattering map. And that is an automorphism, so it's an algebra isomorphism of the uncoupled theory, okay? The one where there are no interactions. Actually not the one you've got in the lab, but a sort of fictitious one that you want to tell counterfactual stories about. One of these counterfactual stories is that we prepare the system and probe independently at early times. And another counterfactual is that we measure the probe at late times. Of course, we don't have separate access. What we have is the single coupled theory. But we tell ourselves a story in which we have at early times the possibility of preparing system and probe independently. And then you can compute what is the expectation value of a late time probe measurement when we set up the system at early times in a state omega tensor sigma, where omega is our system state and sigma is a probe preparation state. And you can calculate what it is. And it turns out that it is the expectation value of some system observable. Remember, B is going to be a probe observable, but the expectation value we get is actually the expectation value of a system observable in the original system state. This system observable is going to be called the induced observable, and there is a formula for it, which it is too hot to explain in great detail. But what I wish you to take away is that it involves the probe observable, it involves the scattering map, and it involves a sort of partial trace going on, which, if I were to give it a tensor product of observables, would just apply the probe preparation state to the probe one and multiply the result by the system factor. Okay, so the story here so far is that if we measure a probe observable, that is equivalent to, or is an effective measurement of the induced system observable. Okay, so that's the measurement scheme. This, when you begin working it through, has a number of very good properties relating particularly to locality and the protection of ignorance, which is a cause dear to my heart. Very much of the time I am ignorant, and very much of the time there are things I wish to remain ignorant of, and some things that I am forbidden by physics from becoming cognizant of. So ignorance has to be protected, and this framework does it. It can also be iterated, because you could say, well, how do you measure the probe? Well, that means introducing another probe, a probe for the probe, and then you need a probe for the probe for the probe. And this whole framework is actually stable under all of that. And for example, there is a recent paper by Mandrisch and Vasquez that shows how you can look at a family of Gaussian modulated POVMs, which is stable under this process. So you can have a whole tower, whole measurement chain where it's Gaussian POVMs all the way up. Now, the inverse problem is rather harder. If you give me a system observable and then say, okay, what probe, what coupling, what probe preparation state is going to give me that induced system observable, then that is difficult, but that's not a surprise because experimental science is quite difficult, and the problem is to work out how you're going to measure what you want to measure. So, on the other hand, there are some results. I just told you that these Gaussian POVMs are stable. So if you want to measure a desired one, there's a formula that tells you what other Gaussian POVM you need to measure, and do that. So that's a nice answer in that framework. What we showed a few years ago was that in a class of models, you can show that every local observable can be obtained as a limit of a sequence of measurement schemes of this type, in which the coupling is taken to 0 as you go down the sequence, and somehow the strength of the observable you're measuring goes up, and what you get is a desired system observable coming out in the limit. But that's a limit, and you could reasonably say, can you do it on the nose? Can you do it exactly? And that's what I'm going to talk about. But first, a bit about states. So I take this to be a fairly basic statement. What is the role of a state? The role of the state is to predict expectation values for measurements. That's its job. So what's the role of an updated state? Well, that's also to predict the results of future measurements, but it is consequent upon earlier ones or other operations, and it will be suitably conditioned on their outcomes. Okay? And from this, it is remarkable and less well known than it should be that the updated state, both in quantum mechanics actually and in quantum field theory, is uniquely determined and may be computed. So Doreen mentioned the book of Paul Bush. The same methodology is applied there and here to compute updated states. And there's another formula that it's a little bit too warm to go into in detail, but I want to tell you that if you want to compute the expectation value of some system observable in a non-selectively updated state, you need to know which observable, you need the scattering map, and there's the probe preparation and the system state. Okay? A closed formula, if you can compute that scattering map. So that's all very well, and there are similar formulae for selective measurements, selective updates, which I'm not going to write down today. There are nice properties. You might have two people doing measurements at space-like separation. And a classic problem in measurement in quantum field theory is who goes first with the update rule, okay? Because, of course, we know in relativity there's no good answer to who is first, and so who goes first is a problem. Well, it turns out that in this framework, those updates can be done in either order or all in one go. Think of it as a sort of super experimenter, okay? One in Naples, one in Sardinia, okay? So then you can compute, that's a good thing about having a formula, you can compute what happens to the expectation values of observables that are localizable space-like to where the first coupling occurred, okay? In non-selective updates, there is no change whatsoever, and that's good because this is an experiment you don't know was happening and you don't know what the outcome was, all right? So your expectation values had better not change, and indeed in this framework they do not change. What about selective ones? Well, there you can check and you can find that the expectation values change, they may change, and in fact the only situation where they don't is when there is no correlation between the observable over here and the induced observable over here in the initial state. This is relating a little bit to the discussion of Bell that we had also with the question. What is happening there is all due to correlations in the initial state, albeit that they are stronger than you can have in a classical theory or a hidden variables theory. Okay. As an application of all of this, you can look at the Sorkin scenario that was briefly mentioned earlier on, and you can show that there are no impossible measurements in this framework. Okay, and that was something I proved with Henning Bostelmann and Maximilian Rupp a few years ago. So I want to emphasize that this was an application. This was a test run of our framework. It was not why we came up with the framework. In fact, we came up with the framework to understand induced observables. And then it was well, while we're in the area, let's think about states as well. Okay. Now, I've talked about states and updated states, but there are good states and bad states in the world, and we only really care about the good states, the ones with good physical properties. And if we're doing, for example, free scalar field theory, there's an answer to the question, what are the good states? And that is the Hadamard class. Okay, so if you don't know quantum field theory in curved space-time, just take it that that's the agreed class of good states. They are also ones whose two-point function looks very much like the Minkowski vacuum two-point function on sufficiently short scales. Okay, they've got the same singularity structure, but of course put into curved space-time. Now this is something that generalizes, and you can generalize it quite a long way, and there's a whole family of models based on decomposable real formally Hermitian green hyperbolic operators, which it is far too hot to describe in detail. So let me just tell you that the last few words there are pronounced Rufko. Okay? If you have hit on the idea of thinking that Rufkos are good and decomposable Rufkos are better, then you can understand what Hadamard means for a very large class of models. It's got Klein-Gordon, it's got multi-component Klein-Gordon, it's got Proctor, it's got gauge-fixed-Maxwell, linearized gravity, all normally hyperbolic operators and all Dirac-type operators, so it's doing quite well. Characteristic of this class is that they can all be quantized by the same basic recipe you use for Klein-Gordon at some level of abstraction. You have an algebra of observables which is generated by smeared fields. Here, they're not scalar test functions anymore, they're sections in a bundle maybe. A very important property is that if I take the direct sum of two Rufkos, I get another Rufko, and when I quantize that, it is the tensor product of what I'd have got from the two individual Rufkos. And you can see that this is not some abstract isomorphism, it's very concrete, The field in the direct sum theory has multi-component now, and if you've got the component which would be a test function for P and a component that would be a test function for Q, then you can write down a formula for the combined field in terms of the original fields, right? So it's very concrete. And you can do Dirac with a little bit of extra structure. And in all of these models, you can say what it means to be Hadamard using microlocal analysis. And that was a breakthrough. It's now heading for 30 years. In fact, Radzikovsky's preprint came out over 30 years ago. This totally revolutionized mathematical quantum field theory in curved space-time. And the most recent expression of it is this treatment of Rufgo's that I did earlier this year. So, the reason for telling you all of this is that one can prove a theorem, which is that the non-selective update of a physical state is physical. And physical means Hadamard. So suppose that the system and the probe and the coupled theory are all described by decomposable Rufgo's. And let's suppose that your initial system state and your initial probe state are Hadamard in the approved sense. Then the theorem is that the non-selectively updated state is also Hadamard. The proof is actually, well, it's got a very simple structure. There's the formula for the non-selective update. What do we see? We see a tensor product of two Hadamard states. So you prove a little result that says tensor product of Hadamard is Hadamard. We see a scattering map. So you prove a little result that says that Hadamard is preserved under scattering maps. And then there is a sort of partial trace, really, because we're throwing away the probe. And another little result is that partial traces of Hadamard states are Hadamard. Okay, so all of these are little results that I proved, and putting them all together, the result is proved the non-selectively updated state is Hadamard, and therefore physical. This, I claim, is good news for the measurement framework. It's also good news for Hadamard states, okay, because it shows that there's an operational side to them. So this is a class that's stable under non-selective measurement. And it shows that these two things that a priori don't have anything to do with each other seem to be talking quite nicely. Okay, so let's see where we have got to. I wrote down a wish list. I think we have dealt with the first one and the last one, and we've got about halfway through the second. Okay, and I've got 2 bullets left, so I'm going to take both bullets together. Because if you've got to take 2 bullets, you might as well take them together. Right. So, let's get on to that. What's the problem? We've got 2 experimenters, Alice and Bob. Their first appearance today, I think, maybe. Anyway. And they are working in space-like separated laboratories and wish to perform experiments on the same algebraic quantum field theory. Now, in AQFT, we know that their observables will commute because they're at space-like separation. So they're commensurable, and therefore, according to usual doctrine, they are simultaneously measurable, whatever that means. But actually, that's not enough for the experiment, because Alice wants to do the experiment in state omega A, and Bob wants to do it in state omega B. Anybody who's a parent has been faced with this problem, okay? Now, so, what can you do about that? Well, Haag and Kastler said, well, perhaps a minimal way of sorting this out is that there should be a state of the whole theory that reduces to Alice's observables as her preferred state and Bob's observables as his preferred state. Okay, good. But actually you want more. You want statistical independence of the results coming out of these 2 experimental laboratories. What you actually want is what's called a local product state. And this is one where if you put in the product of an Alice observable and a Bob observable, the expectation factorizes, okay, into the product of the 2 expectation values. So that's what you want. People have known that for a while, and there are some results that say under certain general conditions you're going to get them, okay? But they don't give very much control over what this product state is. It's more of an existence result. There's another recent result by Co-Sanders who shows that there are Hadamard local product states for the Klein-Gordon field in curved spacetime. But again, it's non-constructive. Okay? It shows that they're there, but not how to quite get them, or not under very much control. So what I'm going to do in the remaining time is describe a result of the following type. Suppose you've got a quantum field theory described by a decomposable RFCO, and you've got some space-like separated laboratories with a little safety margin in between, and two Hadamard states of the whole field theory of your system. And then the result is there is a local product state of these two states on the whole theory, sorry, there's a typo there, which is Hadamard. And on the way to doing this, we're going to solve the problem of the exact measurement schemes. Of course, I did it the other way around. I was trying to solve the exact measurement scheme thing and then thought, while I'm in the area, I could think about states. Okay, I'm going to do this for scalar fields, for simplicity and time, but it works in general, and let's do it. So let's take the Klein-Gordon field, box plus m squared, and the system and the probe are going to be separate copies of this theory. Now we can look at their uncoupled combination. That's their tensor product, which is the same as looking at the sum of the operators. So I've got two copies of a real scalar field. That is the same as the quantum field theory of one complex field. Okay, Z for complex. I'm going to use the fact that there is a global gauge symmetry of the complex field. It's a U1 global gauge symmetry, and it works like this. Feed in a field with a test function, then there's an automorphism of the algebra, which just simply multiplies the test function by your given complex number on the unit circle. The trick is to realize that every one of those can be realized, you realize that it can be realized as a scattering map. This is how it goes. Here's space-time, which as everyone knows is green and orange. And in the past, I choose myself a function from space-time into U1. In the far past, it's going to be my desired complex number Z, and actually I should have said 1 here. It's, of course, the identity of U1 in the far future. In between, whatever you like, smooth though. I'm going to also make the following observation. If I divide by chi, then apply the Klein-Gordon operator, and then multiply by chi, that is also a Klein-Gordon operator, but it's one that is coupled to an external electromagnetic gauge potential, which is even pure gauge. It's given by gradient of chi. And because here chi is constant and there chi is constant, this gauge potential is switched off in the past and in the future. So this, we could use Q as a sort of coupled variant of P. When you compute the scattering map, you find it's this Z. It's as simple as that. It's a direct calculation. So, firstly, now I come to this measurement schemes and state preparation, and I'm first going to do it in a way that would get me thrown out of the hall. All right? Let's use what I just said. For any real number S, I can find a coupled combination of system and probe, each of which is a Klein-Gordon operator, which has a scattering map that sort of rotates you between these two copies, because we've now gone back from the complex picture to two real scalar fields, so your U1 is now a rotation, and this is in fact the formula you get. Don't worry too much about it. The main thing is if I use plus pi by 2, I get a flip from system into, system into probe, and if I use minus pi by 2, I get a flip from probe into system. Okay? So that's what I'm going to do. And I'm now just going to compute the induced observable map for this minus pi by 2. And remember, we have unit tensor probe observable. We now apply this map, which is a flip. So it just turns them round. And then I have to apply this eta thing, which takes the expectation value of that factor, which is always 1, and I just get B. So if you plug in probe observable B, what comes out is the induced system observable is, well, B. Okay? And that shows that you can get any observable you want, because you just measure that one on the probe. So this is a little bit of a kind of a stupid thing, because if you could measure that anyway, then why would you do it like this? But also, and more significantly, it does actually rely on us controlling a whole Cauchy surface. So it's not so good from that perspective. But let's also compute the state update, non-selective update, but using the plus pi by 2, 1. Here's the formula. It's got a tensor unit this time, but I'm using the one that flips them round. I take the expectation value, and what do you know? I get sigma on A. So the non-selectively updated state is just my probe preparation state. Again, if I could prepare this probe state like that, then why would I have to bother with all of this? But worse, again, I need a full Cauchy surface. Okay, so that would get me thrown out. I'm going to do something that I hope doesn't get me thrown out. I'm going to say how we can modify this so that we work with a compact coupling zone. And so instead of using this pure gauge field, okay, I'm just going to multiply it by something. This chi, the psi function rather, is going to be switched on in the purple region and switched off outside. Okay? So that's still an electromagnetic vector potential. It's still 0 in the past and 0 in the future, but now it's 0 on the, spatially, right? We also apply a result that Benito Juarez Aubry and I have proved, which is a sort of localization result for these protocols. It says that, well, you don't have to have exactly the right coupling, you don't have to have exactly the right state, but provided they agree where it matters, you will get what you want where it matters, in a nutshell. So if you do that here, you find that in this space-time picture, with the coupling switched on in this region, if you ask about a probe observable, localizable in the tip of this Christmas tree, you can measure it, right? You haven't anymore got the possibility of measuring all observables with the same scheme, but you can measure all of these ones in that space-time region. And of course, if you want a different space-time region, you get a different Christmas tree, all right? So it's like that. So all observables in some region of space-time admit a measurement scheme with a compact coupling zone. What about state preparation? So again, I take this not very nice global scheme, I multiply the vector potential by a cutoff. I use the localization result. And what comes out is that the non-selectively updated state agrees with the probe preparation state, not everywhere, but in the region that's controlled by this cutoff function, okay? So if your lab is there, if this is Sardinia, right, for the duration of the experiment, 3 or 4 years apparently, hence, yeah, then we can fix it up. I'll fix it up for you. Right? Yeah, a little bit of your funding would help. Yeah. Okay. So, but more than that, outside, in the causal complement of where this coupling is switched on, it's a non-selective update. So expectation values don't change. So where you want it, Sardinia, it changes, okay, to what you want. Everywhere else, it's what it was to start with. Okay. So now let's go back to Alice and Bob. They're space-like separated, and there's a little gap between them. And I now construct these regions, these Christmas trees in space-time as before, and I do it so that Alice's region is space-like separated to where Bob is going to set things up, and vice versa. So if we start with some system state omega and probe preparation state for Alice of sigma A, then Alice's update gets the right state, the one she wants up here, and leaves everything as it was in this region over here, which is where Bob is. So if Bob happened to want that state, it will be good, because you can compute that the state actually is a product state. Okay, I'm not going to go through the calculation, but the main point is it's a product state in the end. So if Bob happened to want the original system state, then that's it. We've got a local product state, but in fact we can do better. What if Bob makes an update as well? So using his preferred state as his preparation, probe preparation state, we've got space-like separation between these coupling regions. And what that means is that the scattering map factorizes. And again, if you do the calculation, it turns out that it is a product state. Whatever the system state was to start with, Alice gets her preferred state, Bob gets his preferred state. A parent's dream, because you kept both of the blighters happy, right? Okay, so summary here is that Alice and Bob make independent, non-selective measurements. Because they're non-selective, if you start with Hadamard, you get Hadamard. So this shows that there are physical local product states, and you can add on some extra adjectives as well, like gauge invariant or quasi-free. And this actually brings me to the end of the talk, because I think I've got a complete run of ticks now down that list. I mean, it's no surprise because I decided what. Right. Okay. So, and then the summary really is that not only do physical local product states exist, they can be prepared, which means the world is safe for experimentalists. Okay. And I want to just close with the thought that these results are interesting in their own right within quantum field theory and curved space-time. But if you go at it as just a strict quantum field theory and curved space-time question, it's hard. If you take an operational viewpoint and think about things in terms of measurements and preparations and use this framework, then actually it becomes tractable. And so that is the thought I will leave you with, and thank you for your attention on a hot morning.
For questions, and I see a forest of R's here. Who was first? Well, Rick.
Thanks for your talk, Chris. So you mentioned that the Hadamard condition is preserved for non-selective measurements, right? Yeah. So I'm assuming that the selective measurements can lead to violations.
So this is actually open, and it's open because I haven't tried. Okay. So there's a technical reason, which is that the algebra I presented doesn't have any effects that are non-trivial. There's obviously, you could use the Weil algebra instead, and I just haven't done that. Okay. I do have a feeling that there could be observables that are a bit nasty. Okay. If you make things out of fields that are smeared with nice smooth things, I don't anticipate any problems, but maybe you could smear with a discontinuous, some non-smooth thing. Then I would not be surprised if Hadamard, or upset particularly, if Hadamard were violated. But it's something that's on the to-do list.
Cool. Yeah, my next question would be, what is the class of observables that does not violate the Hadamard
condition? And then that
condition?
is exactly what you want.
Let us take first there, and then come back down here.
Hi, yeah. So you told us about like this construction when we have like Alice and Bob and they are space like separated. And have you tried making them not space like separated, but like imagine they just, they never got the notice, they didn't know that the other one's also gonna try to prepare a state.
Okay. So in the general measurement framework, there certainly is the possibility of analyzing sequences of measurements where people are not at space-like separation, but there is still enough separation you could put a Cauchy surface in between them. And I can certainly describe the sequence of measurements, a sort of history, if we like, of outcomes that flow from that. And that's what you use when you're analyzing the Sorkin state. In this framework, of course, you can do the calculation, right? You can do the calculation to say, what would you get if Alice does her preparation, Bob does his preparation, but as it happens, Bob is partly in the causal future of Alice. Well, of course, things will be a little bit not what I've got here, because the relevant initial state for Bob, who's now, I suppose, the one that's in the future, would be the one coming out of Alice's update. And that's clean in the region that she controls. It's clean in her spatial complement, causal complement, but you're asking about somebody on the boundary. Okay? And it's not surprising that Bob would now know a little bit about what Alice did. Okay? So you can do the calculation, you just won't get as clean an answer.
Okay, thank you.
You will get an answer.
Is it a good intuition to say that then, like, basically this state wouldn't be a product state, and that would be the main difference?
You're not probably, no, you're not going to get a product state.
Yeah, exactly. Like, is it a good intuition to say that this is the difference, that here we wouldn't have product state and before we had?
The property that it's a product state does use the fact that they're space-like separated. Yeah.
Right, thank you.
Next, Edu, and then we'll come down here.
Thank you for the talk, Chris. Very nice. One of my questions, two questions. One was asked already. Oh, I can do that. Okay, so I had two questions. The first one is very related with what Rick asked. I was thinking I can think in the case of a selective measurement of a counterexample even in flat space-time scalar field theory, but then again it's a bit contrived, and you just said that not. So you expect that they may exist, but in general, no, right? That's what you expect without doing anything?
Well, I mean, if they exist, then in general they exist.
No, what I mean for an arbitrary one that I think of, I can violate it.
With
okay,
an
that's
arbitrary
what I
one,
meant. So the second question would be related to, you mentioned, so there's a lot of interest in physics that happens when you have operations that are localized and they're in regions that are space-like separated, but very close to not. So almost causal contact. And you also mentioned this region, you mentioned that there's a security margin, like some extra, is not quite just space-like separated, but there's some margin, it's more space. I mean, it is quite.
It's a little more than just space.
More than just space-like separated. How important is that for your results?
Well, okay. I mean, from this you can essentially prove the split property, and the split property really is you need that space, that separation.
But can you be arbitrarily close?
So I'm trying to remember a little bit on that one. I think I wouldn't have put it in if it wasn't necessary. Put it like that.
Right.
So I think it is actually. I think to draw these Christmas trees. Yeah, so the point is that, so Alice and Bob are in LA plus and LB plus, right? To do this whole thing, I have to draw a Christmas tree. And in order to do that, I need a little bit more space. But it can be arbitrarily little more space, and then I can fit it, I get very small Christmas trees.
Okay.
Still cost a lot, but yeah, you can do that.
So physically not really relevant in the sense that you can get arbitrarily close. Sorry, maybe we can, sorry about that.
So last question for Chris from down here.
Very quick one. Can we open the window, please?
Yes.
Okay, so my question is related to this whole framework that you have built. At the very beginning, you basically said that you are working in globally hyperbolic spacetimes. Is there a reason to limit yourself to the globally I mean, what happens, how much of this framework survives if you are not working within a globally hyperbolic?
That's a very good question. So what you really need is to be able to solve your equation of motion to get, meaning to have green operators. Right. Now, advanced and retarded, that means if you've got boundaries, you may need to say what happens there. So that's one thing. Next thing you want to talk about Hadamard. Hadamard is somewhat related to propagation of singularities. So you need to now also have an account of what happens if a singularity hits the boundary. It'll probably come off and back into your space-time. You need to have an account for that. If you can supply that, then I think probably everything works. Well, you have to, of course, as always, you have to check a bit. But those are the reasons. And so just to avoid having to worry about any of that, we go globally hyperbolic. Yeah.
Thank you very much again. And we have one more speaker before lunch.
Sono senza tasche, quindi...
Vabbè, anche qui, se tu ti metti da solo non so se fa schifo. Magari...
Aspetta, dov'è? Qua, così.
HDMI o...
Tutte e due, scelta tua. Cos'è HDMI? Facciamo meno HDMI. Ah, ok, aspetta. Wow. Dov'è la presentazione? Com'è se faccio riproduci? Dov'è? Come si fa?
Riproduci?
Però mi sa che poi va avanti da solo.
No.
Speriamo.
So I'll give you warnings for 25-minute mark.
Okay,
and then
perfect.
up to 5 minutes for
Thank you.
Last speaker before lunch, Stefano Cusumano, harvesting stabilizer entropy and non-locality from a quantum field.
So, welcome everybody, and thank you for coming here in this wonderful scenario. So, as already said from the chair, I will talk to you about harvesting stabilizer entropy and non-locality from a quantum field. You can find the manuscript on the archive, and I also warn you that in a couple of days, presumably, a new version will appear on the archive, so stay tuned for that. Before moving into the main content of the talk, let me also acknowledge my collaborators in this work. So Simone Cepollaro, presently a PhD student at Scuola Superiore Meridionale, nearby here. Our postdoc Jovano Davic, and Professor Alyosha Amma. Plus, even though I couldn't find a picture, sorry for that, the master student who started also this work, Giorgio Lo Giudice, who is presently looking for a PhD position, in case somebody's looking for a student. Now, let me give you some outline of this presentation. So we will start by introducing some of the features that we need for this to understand our results. So namely, I will start from accelerated reference frames and the arrow effect and Rindler coordinates before moving to the introduction of the quantum resources that we are interested in, so namely entanglement and non-stabilizerness, which will prove to be fundamental ingredients in order for non-locality. Then I will move to the physical setting of harvesting stabilizer Renyi entropy. So introducing all the physical setting that we are going to analyze. Then we will conclude with the part on non-local correlations and with some further questions on whether it is impossible or possible, before finally give you some conclusions and outlook. So, the arrow effect is a physical effect, according to which an observer in an accelerated reference frame will see the Minkowski vacuum to have the same statistics of a thermal state where the temperature will depend on the acceleration. And this was predicted by Anra, Fielding, and Davis in the 70s. And it is still under the search to observe this effect. Also, this is somehow equivalent to the Hawking radiation in the near horizon of a black hole. To describe an observer in an accelerated reference frame, we use so-called Rindler coordinates, which, as I said, they describe the time and position coordinate in an accelerated reference frame and their relation to the proper time. And we will consider three different scenarios, namely the case of two observers accelerating in the parallel direction, so both in the same direction, then the anti-parallel scenario, so when the two observers are accelerating in opposite directions, and finally in the perpendicular scenario, so where the two observers accelerate in perpendicular directions. And just for completeness, you can observe the coordinates and how they are described. They form a hyperboloid in space-time. Now, these Rindler coordinates define two time-like wedges in space-time, which are often called the left and right wedges. And each of these two is the time reverted of the other. The vacuum state in Minkowski space-time can be expressed as an entangled state with respect to this bipartition of space-time. And the state describing this entangled combination is the thermophile double state. So where we have an entangled state, as you can see from the formula, which has also the property that when looked by a single observer is a thermal state. So if we trace away one of the two parties, we will get a thermal state. So these are the physical ingredients we are going to use. Let us now move to the quantum resources which we are going to use. Let me start from the most known one, which is the entanglement. And of course, as most of you, if not all of you, know, entanglement is an important subject in quantum physics because it's a purely quantum phenomena. And especially when it comes to mixed state, it is also not that easy task to say whether a state is entangled or not, and several measures exist, Fraser series, and many other things. And while several measures exist, in this work we will focus on concurrence, which is a measure based on the positive partial transpose criterion introduced by the Orodetskis in the 90s. And it is important to note also that since we will be dealing with two Unruh detectors described by two-level systems, any measure of entanglement would be equivalent. So even using negativity or logarithmic negativity would lead to the same qualitative results. And in order to compute the concurrence, of course, one has to compute this matrix R, which is the product of the density matrix, and its complex conjugate multiplied by that y operators. And then one considers the eigenvalues of this matrix, takes the largest one, lambda 1, and then subtracts the other three. And if this number is positive, the state is entangled. If not, the entanglement is 0. Let us now move to stabilizer states and non-stabilizerness. So, in order to introduce non-stabilizerness, we need to talk about stabilizer states, and in order to do so, we will introduce the Pauli strings. So, Pauli strings are simply strings of Pauli operators for qubits, each one acting on each qubit. And if we also consider these strings with a phase being plus minus 1 or plus minus I, we get the Pauli group. So it means that if we multiply two of these Pauli strings, we will get a new Pauli string with a phase attached, and the set is closed under this operation. Specifically, we say that an n-qubit state is a stabilizer 1 if there is a subgroup of the Pauli group of cardinality 2 to the power of n, such that the application of the Pauli strings belonging to this subgroup on the state will give 1 times the state. So stabilizer state is an eigenstate of 2 to the power of n Pauli strings. Now the point is that this subgroup S is generated by a set of n Pauli strings, and thanks to this key observation, this means that we can associate to each stabilizer state a set of n generators, each generator being one of the 4 Pauli matrices, so identity x, y, and z. And so we need 2 bits of classical information for each bit, for each qubit. And thus we need essentially polynomial classical resources to describe the state. And so this means that stabilizer states, together with the result by Gottesman that Clifford operations are efficiently classically simulatable, are essentially classically efficient simulatable, and so they're not truly quantum from a computational perspective. Why? Because we can describe them classically. Another ingredient in order to describe stabilizer state and non-stabilizerness is the Clifford group, which is the normalizer of the Pauli group. So essentially it's the set of all operators, unitary operators, which acting by conjugation on the Pauli strings will give you as an output another Pauli string. And we can characterize the set of pure stabilizer states as those states obtained by the application of Clifford operations onto a stabilizer state. Actually, any stabilizer state would work, but we can take as a reference the blank computational state, so the state with all zeros. And the other main important point is that the Clifford group can be generated entirely by the three operators above, which are the Adlam gate, the pi-half phase gate, C0. Also notice that in order to generate the entire unitary group, you actually need also three operators, because you need to substitute the S operator with its square root. So the operator having as matrix elements the 1 and the e to the minus ip fourth on the diagonal. And of course this includes also the ability of generating S as well. Now, the main point is that while one can define, of course, a resource theory of stabilizer states and non-stabilizer states, there are actually only few computable measures of non-stabilizerness, and one that raised much attention in the last couple of years is the stabilizer Renyi entropy, which is this is very important, is efficiently computable for any state. So how one does compute this non-stabilizer stabilizer Renyi entropy? So one defines a probability distribution psi of p, which essentially is some expectation values over the Pauli strings of the state under consideration. And then one takes essentially the Renyi entropy of this probability distribution with the proper index alpha and a normalization given by the dimension of the system, which is 2 to the power n number of qubits. Also, one can define, in a way, non-local version of this stabilizer Renyi entropy, which is essentially the minimum over all multi-local unitaries, so of the form UA tensor UB. So notice that, like entanglement, non-local stabilizer Renyi entropy is defined according to a bipartition. And then one has to minimize over all the multi-local unitaries defined on the bipartition. And finally, one can extend also this measure to mixed states with the formula given above, which is essentially equivalent to the one for pure states, plus some renormalization given by the Renyi entropy of the density matrix, so depending on the purity of the state. This stabilizer Renyi entropy is a good measure from the resource theoretic perspective. Indeed, it is a faithful measure. So a state, a pure state psi, is a stabilizer state if and only if any of its stabilizer Renyi entropy is 0, so all of them, so independently of the alpha chosen. Then this stabilizer Renyi entropy for any index alpha greater than 2 is non-increasing under Clifford operations. So it means that if we apply a Clifford unitary to the state, we will get the same value of the stabilizer Renyi entropy. And it's also additive with respect to tensor product. So if we have a tensor product of two pure states, we simply compute the stabilizer Renyi entropy of the two states and see the reference for further information. Also, before moving to the results, the stabilizer Renyi entropy can be extended to qubit and can also be connected to Wigner negativity. Now, let us move to the physical setting we are going to consider. So we will have two Unruh detectors, which we call A and B. both described as a two-level system, so with the Hamiltonian being given by some frequency omega times the Z operator. And then we will consider also a massless scalar field, so we will put ourselves in a somehow simple scenario, just to start. And we will consider a very common interaction considered in the literature. So namely, we will consider some lambda gauging the strength of the interaction, some function of time, epsilon, describing the time window over which the detectors interact with the field. And then we will have the field operator phi of evaluated at the proper on the proper word line, and also the so-called monopole operator for the detectors. What we will do then is to go into the interaction picture, derive the unitary operators, describing which is just the exponential of the interaction Hamiltonian. We will expand it in power series and then obtain a perturbative expression of the final state. Now, since we are interested in the dynamics of the detectors, what we will do is to trace away the field degrees of freedom and obtain a CPT map describing the final state of the detectors given the input. And this is done by first applying the unitary evolution and then tracing away the field. Now, this map, of course, describes both the interaction of the single detectors with the field and also the interaction between the two detectors induced by the common interaction with the quantum field. And indeed, going up to second order imperturbation theory in lambda, we can derive a perturbative expression for the concurrence and stabilizer Rényi entropy, where, for instance, if we start both detectors in the zero state, so with no excitation, we will get this kind of X-shaped density matrix, from which one can do all the computation and compute the two quantities also up to lambda squared in perturbation theory. And we have that the terms EA squared and EB squared are just the probabilities of each of the detectors being excited. We will have, of course, some coherence, so some overlap between the two excited states of the detectors. And we will have also a non-null probability of the two detectors exchanging a virtual particle. Also notice that while at first glance this might look as a negative density matrix, this is not the case because we are in perturbation theory, so what we need is that this matrix is positive up to the considered perturbative order, and indeed there is a negative eigenvalue, yes, but it's of order lambda fourth, so we are safe in this regard. We start our analysis from an inertial setting, so with two static detectors, where one can also give some analytical results. And what we observe is that as for the concurrence, we get the usual results already known in the literature, while as for the non-stabilizerness, we observe that for it depends only on the product between omega, the frequency of the detectors, and sigma, which is the width of the time window over which the detector and the field interact. Now, the point is that the vacuum state of the field is a stabilizer state from the perspective of the detector. So we shouldn't get any stabilizer Rényi entropy. And indeed, this is not the case, because the non-zero value we are actually observing here depend on the fact that the interaction between the field and the detectors is non-stabilizer. However, so in this way is a fake effect. It's false. It's not harvesting from the field in this setting. It's just the interaction introducing non-stabilizerness in a system which has none. However, we see that for the product of sigma and omega roughly larger than 2, this effect is essentially 0. And so in the accelerated reference frame, we will set our parameters in such a way that we can neglect this spurious non-stabilizerness. Specifically, we first start by studying how this contribution depends on the physical parameters of our system. So first keeping fixed the sigma and the initial distance of the detectors and changing the frequency omega, and then keeping fixed the frequency omega and changing the length L. And in both cases we see first that we confirm all the features of the inertial scenario, so where for large enough values of the product of omega and sigma we get zero contribution, of course, for zero acceleration. And we see, of course, that for lower values we get a higher non-stabilizerness because of the spurious contribution I already cited. While consistently with the inertial scenario, we also see that the non-stabilizerness does not depend on the length, the initial distance L between the two detectors. Then we also study the harvested non-stabilizerness as a function of the initial state of the two detectors. And we observe some common features, so namely that non-stabilizerness is always harvested, plus that this non-stabilizerness is entirely non-local. So it's essentially we can try to minimize it over all possible local unitaries, but nothing happens. Also notice that when the detectors are started in a Bell state, so in a maximally entangled state, naturally the concurrence has to diminish because of we are applying a multipartite unitary, a non-local unitary, and so of course we can only decrease the entanglement. Finally, and I will give you more detail in the next slide, we compute also the difference between the final state and the initial value of the Bell operator B0, which I'm going to show in the next slide. And the main point of this is that we never violate the CHSH inequality. Specifically, we choose the Bell operator in the picture, but we could have chosen any other good one. And the point being that, as we recently found in another manuscript, one cannot violate the CHSH inequality without non-stabilizerness. So if one is consistent with research theory and so consider only free resources of the stabilizer theory, one has that starting from a stabilizer state and applying Clifford operations alone, which I remember you that include the C0, so you can entangle with Clifford operations, it is impossible to get non-local violations. And what we do is simply to compute the expectation value of the operator B0 and check if we can violate. And the result is that we cannot violate because of two reasons. Either we first, if the state is initially maximally entangled, we reduce the entanglement by evolving the state. Secondly, we do not collect enough non-stabilizerness. Third, another result that we found is that you not only need non-stabilizerness in order to violate the CHSH inequality, but you actually need local non-stabilizerness, while we verified that non-local non-stabilizerness is actually bad for violating Bell inequalities in the CHSH scenario. Finally, let me give you some conclusions. So what we have seen is first that we can harvest non-stabilizerness from a quantum field, that the source of this non-stabilizerness is given by the acceleration, and finally that at least in this very simple setting we've used, it is non-possible to collect enough resources to observe non-locality. For the future, of course, one can think of many possibilities. For instance, changing the field, consider massive spinorial fields. You can see we can check different detectors, massive detectors, non-point-like detectors, and all possible variations you can imagine. And it will be also interesting to check if maybe in some smarter settings, one can harvest non-local correlations. This being said, I thank you for the attention, and I hope you enjoyed.
Thank you very much. We have some time for questions. I see a hand over here. Yes? So the microphone is for the recording purposes.
Okay.
People in the room, please shout.
Also because I'm half deaf.
Oh, no. Okay, so I'm wondering how robust is this resource to noise, this non-stabilizerness? Is a resource you were explaining, right?
Mm-hmm.
So I'm wondering how robust it is against types of noise.
What do you mean by noise?
Well, if you have a state that has this resource,
yes.
And it evolves, and you wanna, do something, perform a task, and take advantage of this resource, how fast does it dies or it becomes useless if you expose it to some noise?
So you mean the detectors having some noise?
Yeah, in the environment. If you put some noise in the environment, yeah.
So what you do is you have your detectors interacting with the field in this context. So, and somehow the field is the noise acting on the detectors in a way.
Yeah, but I know, but I mean additionally.
We didn't consider yet this scenario in which you have noisy detectors. So.
But what do you think? Like, do you have any intuition on this resource being robust or?
Well, it depends. It depends on the kind of noise, I would say.
Yeah,
because, of course, depending on how you model the interaction between the environment and the detectors, of course, you might have the same problem that I showed you in the inertial scenario. So where you have an interaction which is non-Clifford, and so, of course, you might get some spurious contribution.
Mm-hmm.
While, of course, if you consider a Clifford interaction between the environment and the detectors, I would say that, yes, this thing is robust. And actually, there is some work going on this with this respect, because it's a delicate point.
Okay. Okay, thank you.
I saw a hand down here.
Yeah.
Ciao. Thank you for the talk. So you mentioned that stabilizer Rényi entropy is a good monotone for, or a faithful monotone for pure states.
For alpha equal or greater than 2.
So we know that for, like, if you pick other monotones for mixed states, you will find different results inside the Bloch sphere, let's say. So in the stabilizer octahedron, you get different results from stabilizer Rényi entropy, mana, and so on. How good is your monotone for mixed states, and how does this extend in other cases in this sense?
So for the point is that the one I showed you is not as good as the linear one, the linearized version, which is just not the log, just the trace of Q rho tensor 4. And in the paper I was citing this Leone and Bittel on Physical Review A. It is actually showed that the linearized version of the stabilizer Rényi entropy, so the one without the logarithm, is also a strong monotone, even for mixed states. While the one with the log is not a strong monotone.
Okay, thank you.
Two more questions, one here and one here.
My question is the following. Can you do the same kind of formalism for the zeta universe?
For the?
For the zeta metric. Because the key point, if I understand correctly, is that you have to have a horizon.
Yes.
And since the typical metric approximately in the early universe is the zeta, and people are trying to understand whether there is some decoherence at which level is not yet understood. When the perturbation of the metric comes from inside the horizon to outside the horizon, depending on the wavelength, the physical wavelength. So it would be interesting to see your discussion in this
I
case.
agree, it would be interesting.
Well, we are in the same department. So.
Yes, we need to study. Sometimes you need to do the thing.
And last question.
Thanks a lot for your great talk.
Please speak up.
Thanks a lot for your great talk.
Thank you.
And I also have something like an outlook type of question. So you were also interested in non-locality, but the field you put in, the field theory you study, is inherently local, right? Because it's a relativistic theory. And I was wondering, have you considered, or do you have an idea, what would happen if you consider something like a long-range type of theory, something that is non-local from the beginning?
So the point is that the answer is not as much in this work, but it's rather in the other one I was citing, because as I briefly mentioned, the point is that you need local non-stabilizerness in order to violate CHSH inequality. So if the field were inherently non-local, still the point is which kind of non-stabilizerness you're harvesting, you're going to harvest. Because in this case, all the non-stabilizerness is due to the fact that the two detectors interact through the field. And so, of course, you get only non-local non-stabilizerness. If you find a possibility to harvest local non-stabilizerness, then you might observe it, but I wouldn't say I wouldn't take for granted that this scenario would change things drastically, in a way, in this respect.
Thank you very much again. Any announcements from the organizers before we break for lunch?
Yes. The first announcement is that working group 4 and 5 of the cost action will meet here for a meeting at 2. So they would have the president the priority in getting lunch and coming here. Yes. The second announcement is that